the scientific method. Before we begin our journey through the most complex theories in physics, we need to understand the process that made those theories possible in the first place. Let me introduce you to the way scientists explore truth, test ideas, and build our understanding of the universe. The scientific method is the foundation of modern science. It's a structured process for asking questions about the world and finding reliable answers through observation, experimentation, and reasoning. At its core, the method begins with a question, often triggered by something unexpected or unexplained. From that question, scientists form a hypothesis, which is a proposed explanation that can be tested. This hypothesis isn't a random guess. It's based on existing knowledge, observations, and logical reasoning. Next comes experimentation. Scientists design controlled experiments to test whether the hypothesis holds up under various conditions. The key is that these experiments must be repeatable. If you follow the same steps, you should get the same result. The data collected during experiments are then analyzed. If the results support the hypothesis, it gains credibility. If not, the hypothesis may be revised or rejected. This process is iterative. You as scientists may return to earlier steps, refine their ideas, and test again. A useful analogy is cooking. Suppose you want to make the perfect pancake. Your question might be, what ratio of flour to milk gives the fluffiest texture? You make a batch with one ratio, test the outcome, adjust, and try again. You control variables like cooking time and pan temperature to isolate the effect of the flour to milk ratio. Eventually, through repeated testing and refinement, you find a recipe that works. That's experimentation, analysis, and revision in action. Importantly, the scientific method does not guarantee absolute truth. It aims for increasing accuracy and predictive power. Even well-established theories are open to challenge if new evidence arises. This is what makes science self-correcting and dynamic. The scientific method is not limited to laboratories. It underpins everything from medical research to engineering to climate modeling. It's the reason we have reliable technology, effective medicine, and an evolving understanding of the universe. By insisting on evidence, logic, and transparency, the scientific method has become one of humanity's most powerful tools, not just for knowing, but for understanding. Classical mechanics. Before quantum mechanics shook our understanding of reality, and before relativity rewrote our view of space and time, there was classical mechanics. This is the branch of physics that explains how objects move under the influence of forces. It was developed between the 17th and 19th centuries, most notably by Isaac Newton, and it remains incredibly accurate for most everyday situations. At its core, classical mechanics is about predictability. If you know the current position and velocity of an object, and you know the forces acting on it, you can predict exactly where it will be and how fast it will be moving at any future time. This idea, often called determinism, is one of the defining traits of classical physics. The fundamental building blocks of classical mechanics are Newton's three laws of motion. An object in motion stays in motion, and an object at rest stays at rest unless acted upon by a force. This law introduces the concept of inertia, the resistance of any object to a change in its state of motion. Force equals mass times acceleration. This is Newton's most famous equation. It means the more force you apply to an object, the more it accelerates, and heavier objects require more force to accelerate at the same rate. For every action, there is an equal and opposite reaction. This law explains why when you push on something, it pushes back. It's why rockets can lift off from Earth by pushing hot gases downward, and why you feel a recoil when firing a gun. These three laws, combined with tools from mathematics, especially calculus, allow us to model an enormous range of phenomena, from the fall of an apple to the orbits of planets, from the swinging of a pendulum to the vibrations of a guitar string. Classical mechanics can describe them all with high precision. Take the motion of planets, for example. When Newton formulated the law of universal gravitation, he realized that the same force that pulls an apple to the ground also keeps the Moon in orbit around Earth and the Earth in orbit around the Sun. Gravity, he proposed, is a force that acts between any two masses. The more massive the objects, and the closer they are, the stronger the gravitational pull. This insight was revolutionary. It unified the physics of Earth with the physics of the heavens. Before that, people thought the laws that governed the skies were different from those on Earth. Newton showed they were the same. To understand classical mechanics more intuitively, consider a game of billiards. Every ball has a mass, and when struck, it moves in a predictable direction, at a predictable speed. If you know the speed, angle, and spin of the cue ball, and the positions of the others, physics allows you to calculate exactly where each ball will go after the collision. No randomness, no uncertainty, just math. This sense of perfect predictability made classical mechanics incredibly appealing. In fact, in the 18th and 19th centuries, many scientists believed that if you could somehow measure all the positions and velocities of particles in the universe, you could, in theory, calculate the future with perfect accuracy. The universe was seen as a giant clockwork machine, running with precision. But classical mechanics has its limits. It fails to explain the behavior of very fast objects close to the speed of light, or very small particles, like electrons. These regimes belong to relativity and quantum mechanics, respectively. Still, for objects moving at everyday speeds and sizes, cars, airplanes, bridges, machines, classical mechanics is not just useful, it's essential. It forms the basis for civil engineering, mechanical design, and aerospace calculations. It powers simulations of cars crashing, skyscrapers swaying in the wind, and satellites orbiting Earth. Classical mechanics is also the entry point into the mathematical language of physics. It introduces concepts like energy, momentum, angular momentum, and conservation laws, principles that reappear in more advanced theories. Even today, physicists, engineers, and mathematicians rely on classical mechanics as a robust, accurate framework for solving practical problems. It's a shining example of how simple rules, applied carefully, can explain a vast array of natural phenomena. It may have been superseded in some domains, but classical mechanics remains one of the most successful theories in the history of science. The atom, everything around you, your body, your screen, the air you breathe, is made of atoms. They are the basic units of matter, and for centuries, scientists have worked to uncover what they are, how they behave, and what lies within them. The word atom comes from the Greek word atomos, meaning indivisible. In ancient philosophy, atoms were thought to be the smallest possible unit of matter, tiny, solid spheres that made up everything in the universe. That idea lingered for centuries, but today we know that atoms are not indivisible at all. They are composed of even smaller particles. An atom consists of a nucleus at its center, containing protons and neutrons, surrounded by a cloud of electrons. Protons carry a positive electric charge. Neutrons carry no charge. They're neutral. Electrons are negatively charged and are much lighter than protons and neutrons. The nucleus is extremely small compared to the whole atom, but contains almost all of its mass. Imagine a football stadium representing an atom, then the nucleus would be a marble sitting at the center, while the electrons would be buzzing somewhere in the outer stands. The number of protons in an atom is called its atomic number, and it defines what element the atom belongs to. Hydrogen has 1 proton. Helium has 2. Carbon has 6. The number of neutrons can vary, creating isotopes, different versions of the same element. The electrons, meanwhile, orbit the nucleus in specific energy levels, or shells. But electrons don't orbit like planets. They behave more like fuzzy clouds, with quantum mechanics determining the probability of finding them in a particular region. This concept is known as an orbital. Instead of fixed paths, electrons are described by mathematical wave functions that tell us where they're likely to be. The structure of atoms determines how they interact. The outermost electrons, called valence electrons, play a critical role in chemical bonding, When atoms share or transfer these electrons, they form molecules. That's how water is made, two hydrogen atoms bonding with one oxygen atom. The modern model of the atom didn't appear all at once. It developed over time, through many experiments and insights. In 1897, J.J. Thomson discovered the electron. In 1911, Ernest Rutherford showed that atoms have a dense central nucleus. In 1913, Niels Bohr proposed that electrons occupy specific energy levels. Later, quantum mechanics replaced Bohr's model with a more accurate probabilistic description. One of the most important ideas in atomic theory is quantization, the fact that electrons can only exist at certain energy levels, not in between. When an electron jumps from a higher level to a lower one, it releases energy, often in the form of light. This explains why different elements emit different colors when heated. It's the basis of spectroscopy, a technique used to identify substances by the light they emit or absorb. Atoms are also incredibly stable. The electromagnetic force keeps the negatively charged electrons attracted to the positively charged nucleus. At the same time, inside the nucleus, a different force, the strong nuclear force, holds protons and neutrons together, overcoming the repulsive force between like-charged protons. Despite their small size, atoms are mostly empty space. If you removed all the empty space from the atoms in every person on Earth, humanity could fit into a sugar cube. This might sound unbelievable, but it reflects how tiny the nucleus is compared to the atom's overall size. Understanding atoms laid the foundation for chemistry, nuclear physics, and quantum mechanics. It led to the development of technologies from electricity and lasers to semiconductors and nuclear power. It also allowed us to unlock the structure of DNA, build microprocessors, and harness radioactivity for medicine and energy. The atom is no longer just a concept, it is a measurable, testable structure at the heart of modern science, and yet, it remains a symbol of wonder. Something so small, so invisible to the eye, is responsible for the structure and function of everything we see. To understand the universe, we must begin with the atom. Wave-particle duality. Wave-particle duality is one of the most surprising and important discoveries in modern physics. It tells us that light and matter don't behave purely like particles, and they don't behave purely like waves either. Instead, they behave like both, depending on how we observe them. Let's begin with light. For centuries, scientists debated what exactly light was. In the 1600s, Isaac Newton believed light was made of tiny particles. Around the same time, Christian Huygens argued that light behaved like a wave, and for good reason. Waves could explain how light reflects, bends, and even interferes with itself, just like ripples on a pond. In the early 1800s, Thomas Young performed a famous experiment that seemed to settle the matter. It's called the double-slit experiment. He passed a beam of light through two narrow slits and observed the pattern it made on a screen. What he saw was not two bright spots, as you'd expect from particles passing through two gaps. Instead, he saw a series of light and dark bands, an interference pattern. This only happens when waves overlap and interfere with each other. It was strong evidence that light is a wave, but then, in the early 1900s, something strange happened. Albert Einstein was studying the photoelectric effect, where light shining on a metal surface causes electrons to be ejected. According to wave theory, increasing the intensity of the light should increase the energy of the ejected electrons. But experiments showed that wasn't the case. Instead, the energy of the electrons depended on the light's frequency, not its brightness. The only explanation was that light sometimes behaved like a stream of particles we now call photons. Each photon carries a fixed amount of energy proportional to its frequency. So now, physicists had a contradiction. Light acts like a wave in some experiments and like a particle in others. It wasn't a matter of either or. Light could behave as a wave or a particle, depending on how it was measured. But it didn't stop with light. Later experiments showed that electrons, particles we normally think of as solid matter, could also create interference patterns. Fire a beam of electrons through a double slit, and the same wave-like pattern appears. Even individual electrons, sent one at a time, gradually build up an interference pattern over time. That means each electron behaves like a wave, interfering with itself. But when you place a detector to see which slit the electron goes through, the interference pattern disappears. The electron acts like a particle again. The act of measuring changes the outcome. This is the essence of wave-particle duality. At the quantum level, particles, like photons, electrons, and even larger atoms, can behave like waves, spreading out, interfering, diffracting, and also behave like particles, appearing in specific places at specific times. The behavior depends on how the system is observed. In mathematical terms, quantum objects are described by wave functions, which encode the probability of finding a particle in a certain state. When not observed, the object exists in a range of possible states, like a wave spread out in space. When measured, the wave function collapses, and the particle takes on a definite position or value. This duality challenges our intuition. In everyday life, things are either one or the other. A baseball doesn't interfere with itself. A ripple on a lake doesn't hit you like a solid object. But in the quantum world, things don't behave that way. There is no clear dividing line between particles and waves. The distinction simply depends on the kind of measurement you make. Wave-particle duality is not just a curiosity. It's at the heart of quantum physics and essential to understanding the behavior of atoms, molecules, and light. It also lays the foundation for quantum technologies, including electron microscopes, lasers, and quantum computers. It reminds us that the universe, at its smallest scale, does not follow the logic of everyday experience. Instead, it follows rules that are strange, counterintuitive, and yet incredibly precise. And wave-particle duality is one of those rules. The Standard Model. The Standard Model is the most successful theory we have to describe the fundamental building blocks of the universe and how they interact. It explains what everything is made of and how the tiniest components of matter communicate through fundamental forces. According to the Standard Model, all matter is made up of a few basic types of particles, and all forces, except gravity, are the result of the exchange of other particles. In total, the theory includes a set of particles known as fermions, force carriers called bosons, and one special particle that gives others mass, the Higgs boson. Let's start with matter. All matter is made of fermions, which come in two categories, quarks and leptons. Quarks are what make up protons and neutrons. Leptons include electrons, as well as the less familiar muons and tau particles, plus their ghost-like cousins called neutrinos. There are 6 types of quarks: up, down, charm, strange, top and bottom, and 6 types of leptons: the electron, muon and tau, along with their 3 matching neutrinos. Each of these particles has a corresponding antimatter partner with the same mass but opposite charge. Next are the bosons. These are the particles that carry forces. The photon is the carrier of the electromagnetic force. Gluons carry the strong nuclear force, which holds quarks together inside protons and neutrons. The W and Z bosons carry the weak nuclear force, which is responsible for radioactive decay and nuclear fusion. And finally, the Higgs boson, discovered in 2012, is linked to the Higgs field, a field that gives mass to other particles. All of these particles interact in precise and predictable ways. The photon allows charged particles to feel electric and magnetic forces. Gluons keep atomic nuclei intact, while in Z bosons allow certain particles to transform, enabling fusion in the Sun, and the Higgs field slows particles down, giving them inertia, what we experience as mass. The Standard Model has been tested countless times in experiments, especially in particle accelerators like the Large Hadron Collider. These machines smash particles together at incredibly high speeds, recreating the conditions of the early universe. The debris from those collisions reveals the behavior of particles at the most fundamental level. Time after time, the predictions of the Standard Model have matched the results with extraordinary precision. One of the key features of the Standard Model is how it combines quantum mechanics and special relativity into a single mathematical framework called quantum field theory. In this view, particles are not little dots, but excitations in underlying fields. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. What we call particles are just tiny packages of energy moving through space. Despite its success, the Standard Model is incomplete. It does not include gravity. It does not explain dark matter or dark energy. It cannot tell us why the masses of particles have the values they do, or why the universe contains more matter than antimatter. It also doesn't include neutrino masses, which we now know exist thanks to the discovery of neutrino oscillations. Nevertheless, the Standard Model is the most complete and accurate description we have of the subatomic world. It explains why atoms exist, why chemical reactions happen, and why stars shine. It forms the backbone of particle physics and provides the groundwork for much of modern technology. Think of it as a kind of periodic table for the universe, not for elements, but for the ingredients of reality itself. It doesn't explain everything, but what it does explain, it does with astonishing accuracy. And until a more complete theory emerges, the Standard Model remains the best map we have of the quantum world. Quantum mechanics. Quantum mechanics is the branch of physics that describes how the universe behaves at the smallest scales, on the level of atoms, electrons, and photons. It is a framework that does not follow the rules of everyday experience. Instead, it operates according to its own set of principles, where probability replaces certainty, and reality behaves in ways that often seem strange or unintuitive. In classical mechanics, if you know an object's position and velocity, you can predict exactly where it will be at any moment in the future. But in quantum mechanics, particles do not have definite positions or velocities until they are measured. Instead, they are described by a mathematical object called a wave function. The wave function gives a probability distribution. It tells us where the particle is likely to be, not where it actually is. This is one of the central ideas of quantum mechanics. Before measurement, a particle does not have a specific position. It exists in a superposition of possibilities. When we make a measurement, the wave function collapses, and the particle takes on a definite value. This is not due to measurement error or a lack of information. It's a built-in feature of how nature works at small scales. The mathematics of quantum mechanics is precise, but the results are probabilistic. You can calculate the likelihood of a particle being in a certain place or having a certain energy, but you cannot predict the exact outcome with certainty. The best you can do is describe the odds. This probabilistic nature of quantum mechanics was famously unsettling to many physicists. Albert Einstein, for example, once said, "God does not play dice with the universe, but experiments have consistently supported quantum mechanics. Nature does seem to play dice, though it follows very strict rules when doing so." Another essential feature of quantum mechanics is quantization. Certain properties, like energy, do not take on a continuous range of values. Instead, they come in discrete steps, or quanta. And for instance, an electron in an atom can only occupy specific energy levels. It cannot exist between them. When it jumps from a higher level to a lower one, it emits a photon with a specific energy, which corresponds to a particular color of light. This idea explains the spectral lines we see in the light from stars, and it's the foundation of quantum chemistry. One everyday analogy for quantum uncertainty is a blurry photo. Imagine trying to take a picture of a fast-moving object in low light. The faster it moves, the harder it is to capture its position clearly. The more you try to sharpen the motion, the more you lose clarity on where it is. This is similar to the Heisenberg uncertainty principle, which says that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Quantum mechanics also introduces the idea that particles can behave like waves. This wave-like nature leads to interference patterns, tunneling effects, and the ability for particles to be entangled, a concept explored in other chapters. Despite its strange behavior, quantum mechanics is one of the most successful theories in all of science. It accurately predicts the outcomes of countless experiments and is responsible for much of the technology we use today. Transistors, lasers, magnetic resonance imaging, atomic clocks, and even the chips in your phone all rely on principles from quantum mechanics. It is not an optional or fringe theory. It is the operating system of the universe at small scales. It replaces the certainties of classical physics with probabilities, but it does so with extraordinary precision. Quantum mechanics may seem abstract, but it is the reason atoms form, molecules exist, and light interacts with matter. Without it, chemistry would not work, and the stars would not shine. Understanding it is essential to understanding the structure and behavior of the universe itself. Heisenberg Uncertainty Principle. The Heisenberg Uncertainty Principle is one of the core ideas of quantum mechanics, and it reveals something profound about the limits of what we can know. It tells us that there are certain pairs of physical properties that cannot be measured precisely at the same time. The most famous pair is position and momentum. Momentum is simply mass times velocity. So knowing a particle's momentum means knowing how fast it's moving and in what direction. Position, on the other hand, is knowing exactly where the particle is in space. In classical physics, you could in principle measure both perfectly, but in quantum mechanics, there's a fundamental limit. The more precisely you try to measure a particle's position, the less precisely you can know its momentum. And the more precisely you know its momentum, the less certain you are about its position. This is not due to faulty instruments or experimental error. It is a built-in feature of reality at the quantum level. Mathematically, this relationship is expressed as follows. The uncertainty in position multiplied by the uncertainty in momentum must be greater than or equal to a very small number known as the reduced Planck's constant divided by 2. In spoken form, that means delta x times delta p is greater than or equal to h bar divided by 2. Here, delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is the reduced Planck's constant. This equation sets a lower bound. You cannot reduce the uncertainty below this limit, no matter how advanced your technology is. It is not a matter of better measurements. It is the nature of the system itself. To understand this more intuitively, imagine trying to photograph a tiny object in a dark room. You shine a beam of light on it to see it better. But light carries energy, and when you use shorter wavelengths to get a clearer picture, you also increase the energy of the photons you're using. These higher energy photons push the object around as you try to observe it, making its motion less certain. The more clearly you try to see where the object is, the more you disturb how it's moving. This is similar to how measurement affects quantum systems. Another way to look at it is to imagine a guitar string. If you pluck it softly, the note you hear is spread out and a little vague. But if you force the string to vibrate at one precise frequency, its position becomes less well-defined. The same trade-off happens in the quantum world between position and momentum. This principle doesn't just apply to electrons or photons. It applies to all quantum systems. And while the effects are negligible at human scales, they become crucial when dealing with atoms, molecules, and subatomic particles. The uncertainty principle is also the reason why particles don't simply collapse into a single point. If electrons could sit motionless right on top of atomic nuclei, atoms wouldn't exist. But because trying to pin down their position would lead to enormous uncertainty in their momentum, electrons remain in a kind of fuzzy cloud around the nucleus. This gives atoms volume and ultimately gives matter structure. It also explains why zero-point energy exists. Even at absolute zero, particles still have some motion. That's because if they were perfectly still, their momentum would be exactly zero. and their position would be perfectly known, something forbidden by the uncertainty principle. This principle is not just a limitation. It reveals something deeper about how the universe operates. It tells us that the act of observation is not passive. At the quantum scale, to observe is to disturb. To know one thing precisely is to unknow another. The Heisenberg uncertainty principle reminds us that nature does not yield all its secrets freely. There are limits to what we can predict, and in those limits, we glimpse the true nature of quantum reality. Quantum entanglement. Quantum entanglement is one of the most fascinating and puzzling phenomena in all of physics. It describes a situation where two or more particles become linked in such a way that the state of one particle is directly connected to the state of another, even if they are separated by vast distances. To understand what this means, we need to recall that in quantum mechanics, particles like electrons and photons are described by wave functions. These wave functions can represent a range of possible outcomes. When two particles become entangled, their wave functions are no longer separate. Instead, they form a combined system. The properties of the two particles become correlated in a way that cannot be explained by classical physics. For example, imagine two particles are created together in a special process, such as the decay of a single particle. Their properties, like spin or polarization, are connected. If one particle ends up with spin up, the other must be spin down. But until a measurement is made, neither particle has a definite spin. They exist in a shared superposition, where both outcomes are possible. Now suppose you send one of the particles to one side of the universe and the other to the opposite side. When you measure the spin of the first particle, it instantly determines the spin of the second, no matter how far apart they are. It's as if information has traveled faster than the speed of light. But nothing physical is transmitted between them. Instead, the two particles are part of a single indivisible quantum system, even when they are separated by great distance. This idea was so strange that even Albert Einstein doubted it could be true. He called it spooky action at a distance, and believed that there must be some hidden variables, some unknown factors that would explain the results in a more familiar, local way. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper now known as the EPR paradox. It questioned whether quantum mechanics was a complete theory. But in the 1960s, physicist John Bell developed a mathematical test, now called Bell's theorem, to settle the question. If hidden variables existed, certain statistical outcomes would be limited. But if entanglement was real, the predictions of quantum mechanics would break those limits. Over the years, experiments have consistently confirmed the predictions of quantum mechanics. Entanglement is real, and no hidden variables have been found to explain it in a classical way. Importantly, entanglement does not allow for faster-than-light communication. You can't use it to send messages or signals instantly. The results are fundamentally random, and only when you compare measurements later do you see the correlations. But the existence of those correlations defies our classical expectations and reveals something deep about the nature of information in quantum systems. One way to think about entanglement is like a pair of gloves. If you put one glove in a box and send it to the other side of the world, and then open the box here to find a left glove, you instantly know the other box contains the right glove. But the difference is that, with entangled particles, the gloves are not left or right until you look, and the outcome of the first measurement affects the state of the second, even though they were far apart and no signal passed between them. Entanglement has practical applications too. It's being used in quantum cryptography, where the presence of an eavesdropper disrupts the entanglement and reveals that a message has been compromised. It's also central to quantum computing, where entangled particles can represent multiple states simultaneously, allowing for powerful parallel processing. But beyond technology, entanglement forces us to rethink what we mean by separation, independence, and even space itself. It suggests that the fabric of reality is more interconnected than our everyday experience would suggest. But at a fundamental level, the universe is not made of isolated parts, but of deeply linked systems. Quantum entanglement is not magic. It is a measurable, testable phenomenon, but it is a reminder that the universe is not built according to our intuition. It is built according to quantum rules, and those rules often challenge what we think is possible. Quantum superposition. 2. Quantum superposition is one of the most important and unusual features of quantum mechanics. It refers to the idea that a quantum system can exist in multiple possible states at the same time until it is measured. To understand this concept, imagine a coin spinning in the air. While it spins, it's not strictly in a heads or tails state. It's in motion, not yet collapsed into one outcome. But in quantum mechanics, it goes further than that. A quantum particle, such as an electron, can literally be in a combination of different states simultaneously. It's not just uncertain, it truly exists in a superposition of possibilities. Take an electron's position as an example. Before we measure it, the electron is not in one specific location. Instead, it exists in a superposition of all the places it could be. The wave function, which describes the electron, includes all of these possibilities. When we perform a measurement, the wave function collapses and the electron appears at one specific point. This is very different from classical physics, where objects are always somewhere. In the quantum world, particles do not have definite properties until they are observed. Until that moment, they exist in a blend of all allowed states. This strange idea was highlighted in a famous thought experiment proposed by physicist Erwin Schrödinger. He imagined a cat sealed inside a box, along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat lives. But according to quantum mechanics, until the system is observed, the atom is in a superposition of decayed and not decayed, and the cat, bizarrely, is in a superposition of alive and dead. Of course, Schrödinger never intended this to be taken literally. The point of the thought experiment was to show how strange quantum principles become when extended to larger objects. But it illustrates the idea of superposition clearly. A system can remain in multiple potential states until something causes it to choose one. Superposition is not just theoretical. It has been confirmed through many experiments. In the double-slit experiment, a single particle, such as an electron, can interfere with itself by going through both slits at the same time. This can only happen if the particle exists in a superposition of both paths. Once you try to measure which path the particle takes, the superposition collapses and the interference pattern disappears. One helpful analogy is music. Think of a chord played on a piano. It is not a single note, but a superposition of several notes sounding together. The wave function of a quantum particle is like a chord made up of many possible outcomes. When we listen, or in the case of physics, when we measure, we hear one specific note. The others vanish. Superposition also plays a crucial role in quantum computing. Unlike classical bits, which can be either 0 or 1, quantum bits, called qubits, can exist in a superposition of 0 and 1 at the same time. This allows quantum computers to perform many calculations in parallel, offering enormous potential for speed and power. But superposition is fragile. It is easily destroyed by interaction with the environment, a process called decoherence. That's why maintaining superposition is one of the biggest challenges in building practical quantum computers. The principle of superposition is at the heart of the quantum view of reality. It tells us that nature does not commit to one possibility until it has to, that the universe at its smallest scale is not fixed or definite, but fluid and probabilistic. It may sound strange, even unsettling, but superposition is not a flaw in our understanding. It is a fundamental feature of how the quantum world operates, and without it, the world we know could not exist. Schrödinger's cat. Schrödinger's cat is one of the most famous thought experiments in physics. It was proposed in 1935 by the Austrian physicist Erwin Schrödinger, not to explain quantum mechanics, but to question it, to point out how strange and counterintuitive its implications can become when applied to everyday objects. The setup is simple, but unsettling. Imagine placing a cat inside a sealed box. Alongside the cat, there is a tiny amount of radioactive material, a Geiger counter to detect if the atom decays, a vial of poison, and a hammer rigged to break the vial if the Geiger counter goes off. The key is that the atom has a 50% chance of decaying within a certain period. If it decays, the detector is triggered, the hammer breaks the vial, and the poison is released, killing the cat. If the atom does not decay, nothing happens, and the cat survives. Now here's the twist. According to quantum mechanics, the atom does not simply decay or not decay before you check. It exists in a superposition of both decayed and not decayed states. And because the detector, the hammer, the vial, and the cat are all part of the same system, they too become entangled in this uncertainty. So, until someone opens the box and looks, the entire system is in a superposition. The atom is both decayed and not decayed, and by extension, the cat is both alive and dead at the same time. Of course, in reality, no cat has ever existed in this kind of state. Schrödinger never intended for this to be taken literally. His goal was to show how absurd the implications of quantum mechanics can seem when applied to larger systems. The idea that something could be alive and dead at once is meant to make us pause. It's not just about the cat, it's about what it means for a system to have a definite state at all. This leads to deeper questions about the role of observation in quantum physics. When exactly does the wave function collapse? Is it when a conscious observer checks the system, or is it when the quantum system interacts with the environment? Does the act of opening the box cause the cat to become either alive or dead? Or does the cat's fate become fixed earlier, perhaps when the atom decays, or doesn't? Some interpretations of quantum mechanics suggest that the act of measurement causes the collapse. Others propose that all outcomes actually occur, but in separate branches of the universe. According to this many-worlds interpretation, when the box is opened, the universe splits. In one universe, the cat is alive. In another, the cat is dead. Both outcomes are real, but they exist in parallel versions of reality. This might sound like science fiction, but it is one of the leading ways physicists try to make sense of quantum behavior without relying on a special role for the observer. Regardless of interpretation, Schrödinger's cat remains a powerful tool for thinking about the limits of quantum theory. It reminds us that quantum effects, which dominate at small scales, usually disappear when we move to larger systems. This transition from the quantum world to the classical world is still not fully understood. It's part of what makes quantum mechanics so rich and challenging. In the end, the point of the thought experiment is not to imagine a half-dead cat. It's to confront a deeper question. What does it mean for something to be real? And when does possibility become reality? Schrödinger's cat forces us to grapple with the strange nature of observation, measurement, and reality itself in the quantum world. It highlights the gap between what the theory predicts and what we're used to seeing, and it shows us that sometimes the most powerful scientific ideas are the ones that leave us with more questions than answers. Quantum tunneling. Quantum tunneling is a phenomenon that seems impossible at first glance. It describes how a particle can pass through a barrier that it does not have enough energy to climb over. In classical physics, this would be like a ball rolling toward a hill, slowing down, and then somehow appearing on the other side without ever going over the top. But in the quantum world, this happens all the time. To understand why, we need to look at how particles behave in quantum mechanics. Unlike classical objects, quantum particles are not localized at a single point. They are described by wave functions, which give the probability of finding the particle in different places. These wave functions can spread out over space, and importantly, they don't stop at the edge of a barrier. Let's say an electron is approaching a wall of energy, a potential barrier. If the barrier is higher than the electron's energy, classical physics says the electron must bounce back. It doesn't have enough energy to overcome the hill. But in quantum mechanics, the wave function describing the electron extends into the barrier. The further it goes, the more the wave function fades. However, if the barrier is thin enough, the wave function doesn't drop to zero before reaching the other side. That means there is a non-zero probability that the electron will appear on the far side, as if it passed through the wall. This is quantum tunneling. The particle does not climb the barrier. It tunnels through it, and it does so without violating any laws of energy conservation. The key is that in quantum mechanics, the rules are not about definite paths, but about probabilities. One everyday analogy is a car stuck in a valley between two hills. In classical physics, the car would need to gain enough speed to drive over the hill. If it doesn't, it rolls back down. But in quantum mechanics, there's a small chance that the car could appear on the other side of the hill, even though it never went over the top. It sounds strange, but it's real. Quantum tunneling is not just a theoretical curiosity. It plays a critical role in many physical processes. For example, in the core of the Sun, nuclear fusion is made possible by tunneling. Protons inside the Sun are positively charged, and they repel each other. At the temperatures in the Sun, they don't have enough energy to overcome this repulsion, yet fusion still occurs. That's because quantum tunneling allows them to get close enough for the strong nuclear force to take over and bind them together. Tunneling is also the reason why certain kinds of radioactive decay happen. In alpha decay, the nucleus ejects a helium nucleus, called an alpha particle. The alpha particle is trapped inside a potential barrier formed by the strong nuclear force. But it can escape by tunneling through the barrier, even though it doesn't have enough energy to break free in the classical sense. This effect also shows up in modern technology, in tunnel diodes, and certain types of transistors. Electrons tunnel through thin layers of material to create electric current. This allows for faster switching speeds in electronics. Scanning tunneling microscopes use the tunneling effect to image surfaces at the atomic level. They bring a sharp tip extremely close to a surface, and the electrons tunnel between them. By measuring this tunneling current, scientists can see the shapes of individual atoms. The probability of tunneling depends on both the height and the width of the barrier. A thicker or taller barrier reduces the chance. But even then, the probability never drops to zero. That's one of the key differences between classical and quantum thinking. In classical physics, if something is impossible, it's strictly forbidden. In quantum mechanics, many things are not impossible. They're just very unlikely. Quantum tunneling reminds us that particles are not like tiny billiard balls, following strict paths. They are better described as waves of possibility, and sometimes those possibilities include passing through barriers that classical logic says should stop them. It's a powerful demonstration of how the quantum world operates on rules that are unfamiliar to us, yet measurable, testable, and deeply real. Quantum field theory. Quantum field theory is the framework that brings together quantum mechanics and special relativity. It is the most complete and accurate description we have of how particles and forces behave at the smallest scales, and it changes the way we think about what particles really are. In classical physics, we imagine particles as small, solid objects, tiny balls that move through space. But in quantum field theory, particles are not separate things moving through empty space. Instead, they are excitations, or ripples, in underlying fields that extend throughout the entire universe. Every type of particle is associated with a field. There is an electron field, a photon field, a quark field, and many others. These fields are present everywhere, even in empty space. What we call a particle is just a localized disturbance in one of these fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. The ripple travels through space, and we observe it as a particle. This idea is powerful because it unifies the world of particles and forces. In this framework, forces arise from the interactions between fields. For example, the electromagnetic force is carried by photons. When two charged particles interact, they exchange photons. These photons may be real, like the light we see, or they may be virtual, temporary disturbances in the field that appear during interactions, but cannot be directly observed. The same is true for other forces. The strong nuclear force is carried by gluons, which are associated with the gluon field. The weak nuclear force is carried by the W and Z bosons, and the Higgs boson is the ripple in the Higgs field, which gives mass to other particles through its interaction with them. One of the most important aspects of quantum field theory is that it allows for the creation and destruction of particles. In quantum mechanics, particles are usually conserved, but in quantum field theory, energy can be converted into particles, and vice versa, as long as the conservation laws are respected. This is why high-energy collisions, such as those in particle accelerators, can create new particles from pure energy. The theory also explains the presence of virtual particles, temporary fluctuations that appear and disappear too quickly to be observed directly, but that influence the behavior of real particles. These virtual particles are part of the background quantum fields, and they contribute to processes like force interactions, energy shifts, and even the structure of empty space. Quantum field theory uses a mathematical tool called Feynman diagrams to represent particle interactions. In these diagrams, lines represent particles, and points where lines meet represent interactions. They provide a way to visualize and calculate the probabilities of different outcomes in complex particle processes. One of the biggest successes of quantum field theory is the development of quantum electrodynamics, or QED. This is the field theory that describes how light and matter interact. It has been tested to extraordinary precision and has produced some of the most accurate predictions in all of science. The theory correctly predicts, for example, the magnetic moment of the electron to a level of agreement with experiments that is better than 1 part in a billion. Quantum field theory also underlies the standard model of particle physics, which describes all known fundamental particles and their interactions, except for gravity. The standard model is built entirely within the framework of quantum fields. Despite its success, quantum field theory is incredibly complex. The calculations often involve infinities that must be carefully removed using a method called renormalization. This process adjusts the equations in a consistent way to produce meaningful, finite results. It may sound like a trick, but it works, and it has been validated by decades of experimental data. Quantum field theory also leads to strange consequences, such as the idea that empty space is not really empty. Even in a perfect vacuum, the fields continue to fluctuate. These fluctuations give rise to what is called vacuum energy, a subtle but measurable effect that contributes to phenomena like the Casimir effect, and may even play a role in the expansion of the universe. In essence, quantum field theory tells us that the universe is not made of isolated particles, but of continuous fields vibrating across space and time. Particles are just the visible peaks in those vibrations, and the interactions between particles are simply the way those fields talk to each other. It is a deeply abstract, yet incredibly precise way of looking at nature, and it has become the foundation of modern theoretical physics. Virtual particles. Virtual particles are one of the strangest and most misunderstood ideas in quantum physics. They are not particles in the traditional sense. You cannot see them or detect them directly. They don't exist in the way real particles do, and yet their presence is essential for explaining how forces work at the quantum level. To understand virtual particles, we first need to remember how quantum field theory describes the universe. In this theory, every particle is a ripple in a field that fills all of space. When particles interact, when they push or pull on each other or change direction, it is because something has passed between them. that something is often a virtual particle. Take the electromagnetic force as an example. When two electrons repel each other, it's not because they're physically touching. According to quantum electrodynamics, they are exchanging photons, the carriers of the electromagnetic field. But these are not regular photons, like the ones that make up visible light. They are virtual photons. A virtual particle is a temporary disturbance in a field. It appears during an interaction and disappears immediately afterward. It does not satisfy the usual energy and momentum relationships that real particles follow. That's why it can only exist for an extremely short time. The uncertainty principle allows this brief violation. It says that the more uncertain we are about a particle's energy, the shorter the time that energy can exist. So virtual particles are allowed to pop in and out of existence, as long as they don't stick around for too long. You can think of virtual particles as the messengers of forces. They exist in the middle of a process. They are never observed directly, but they are essential for calculating the outcomes of particle interactions. In fact, the probabilities for these processes are calculated using diagrams called Feynman diagrams. In these diagrams, the straight lines represent real particles, and the internal lines, often loops or wavy connectors, represent virtual particles. Virtual particles are not just limited to electromagnetism. They appear in all quantum field theories. In the strong force, quarks inside protons and neutrons constantly exchange virtual gluons. In the weak force, particles like electrons and neutrinos exchange virtual W and Z bosons. And even the Higgs mechanism, which gives particles mass, involves virtual interactions with the Higgs field. One of the most surprising consequences of virtual particles is that they can influence what we think of as empty space. In quantum field theory, even a perfect vacuum is not truly empty. Fields continue to fluctuate, and these fluctuations give rise to virtual particles. These particles appear in pairs, interact, and vanish almost instantly, but their effects are real. For example, the Casimir effect is a force that arises between two closely spaced metal plates in a vacuum. It has been measured in the lab. The explanation involves virtual particles. Between the plates, fewer modes of virtual particle fluctuations can exist than outside. This imbalance creates a tiny pressure that pushes the plates together. Virtual particles also affect the energy levels of atoms. In hydrogen, for instance, the interaction of the electron with virtual particles in the vacuum slightly shifts its energy. This shift, known as the Lamb shift, has been measured with high precision and agrees perfectly with the predictions of quantum electrodynamics. So while virtual particles are not real in the traditional sense, they don't exist on their own, and they cannot be detected directly. They are not imaginary either. They are a useful mathematical tool that captures the behavior of quantum fields during interactions, and the predictions based on virtual particles match experimental results with astonishing accuracy. It's important to remember that the term virtual is not meant to imply that these particles are fake. It simply means they are part of the internal workings of a quantum interaction. They help describe what happens between the start and end of a process, even if they don't leave any trace behind. Virtual particles are a reminder that the quantum world is not made up of solid, self-contained objects moving through empty space. Instead, it is a dynamic landscape of fields, fluctuations, and possibilities, where even emptiness is alive with invisible activity. Bell's theorem. Bell's theorem is a milestone in the foundations of quantum physics. It addresses one of the deepest questions in science, whether the universe is fundamentally local and deterministic, or whether quantum entanglement truly defies classical explanation. To understand the significance of Bell's theorem, we need to go back to a debate that began in the early 20th century. When quantum mechanics was first developed, it introduced strange ideas like superposition, uncertainty, and entanglement that didn't sit well with everyone, including Albert Einstein. He believed that quantum mechanics, while successful in practice, was incomplete. There must be some hidden variables, some underlying factors that restore order and determinism to the theory. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper now known as the EPR paradox. They argued that quantum mechanics allowed for spooky action at a distance, entanglement between particles that could instantly affect each other, no matter how far apart they were. To them, this was unacceptable. They believed that either the particles had pre-existing values, that is, hidden variables, or quantum mechanics was flawed. This is where John Bell comes in. In 1964, Bell developed a mathematical argument that made the issue testable. He showed that if hidden variables existed, and if the universe were local, meaning that information could not travel faster than the speed of light, then certain statistical relationships, called Bell inequalities, must hold. On the other hand, if quantum mechanics was correct, and entanglement was real in the way the theory predicted, then those inequalities would be violated. What Bell's theorem provided was a way to distinguish between two worlds, one governed by local realism and one governed by the non-local probabilistic rules of quantum mechanics. The next step was to test these predictions in the lab. Starting in the 1970s and continuing into the 21st century, physicists performed increasingly precise experiments to test Bell's inequalities. They used pairs of entangled photons, measured their polarizations at different angles, and compared the results. Over and over again, the results supported quantum mechanics. The Bell inequalities were violated, just as the theory predicted. These outcomes strongly suggest that the universe is not both local and deterministic. At least one of those assumptions has to go. So what does this mean? First, it tells us that hidden variable theories that try to preserve classical intuition cannot explain quantum behavior, at least not without giving up on locality. And second, it confirms that entangled particles behave in a way that is genuinely non-local. The outcome of a measurement on one particle is instantly correlated with the outcome on the other, no matter the distance between them. It's important to understand that this does not mean information is traveling faster than light. No usable signal can be transmitted in this way, and causality is preserved. But it does mean that the results of quantum measurements cannot be explained by any local mechanism that existed before the measurement was made. Bell's theorem also raises deep philosophical questions. If the universe is not local, then space and time may not be as fundamental as we think. The apparent separation between distant objects may be an illusion, at least at the quantum level, and if we give up on determinism, then the outcomes of quantum events are not fixed in advance. They emerge only when measured. Some interpretations of quantum mechanics try to make sense of these results by proposing a multiverse or by redefining what we mean by measurement. Others accept non-locality as a basic feature of reality. But what all interpretations must agree on is that Bell's theorem has changed the way we think about the nature of the universe. It provides strong evidence that quantum mechanics is not just a useful tool, it is a fundamentally correct description of nature, even if that nature is very different from what our classical minds expect. Bell's theorem doesn't just close the door on hidden variables. It opens a window into the deeper structure of reality, a structure where entanglement is real, locality is limited, and the universe is more interconnected than it appears. Quantum decoherence. Quantum decoherence is a concept that helps explain why the strange behavior of quantum particles isn't something we see in everyday life. It's not about how the quantum world stops being quantum. Instead, it's about how quantum possibilities become classical outcomes. It shows us how superpositions collapse, not through measurement alone, but through interaction with the environment. In quantum mechanics, a particle doesn't have a definite state until it is observed. It exists in a superposition of all the states it could be in, but as soon as you measure it, the wave function collapses, and the particle takes on a definite value. That's the textbook explanation. But it leaves a big question: what exactly counts as a measurement? Quantum decoherence offers a deeper explanation. It says that what causes the wave function to collapse is not necessarily a human observer or a measuring device. Instead, It's the particle's interaction with its surroundings, air molecules, photons, other particles. When a quantum system becomes entangled with the environment, the coherence between its possible states is lost. That's what we call decoherence. To understand this, imagine a spinning coin again, suspended in the air. In a quantum superposition, the coin is not just heads or tails, it's both at once. But now imagine the air around it, jostling the coin slightly, or light bouncing off it, or vibrations from the floor creeping in. All these interactions carry away tiny bits of information about the coin's state. They leak information into the environment, even if no one is watching. As a result, the quantum superposition begins to unravel. The system loses its ability to interfere with itself. That's decoherence. Importantly, decoherence does not select a specific outcome. It doesn't say whether the coin ends up as heads or tails. What it does is destroy the interference between the two possibilities. It makes the system behave as if it has chosen a single state, even though in the full quantum description, it may still be entangled with the environment in a more complicated way. This process happens incredibly fast. For a small particle in a typical environment, decoherence can occur in a fraction of a nanosecond. For larger objects, it happens even faster. That's why we never see macroscopic objects, like baseballs or cats, in visible quantum superpositions. They're constantly interacting with the environment, and decoherence wipes out their quantum behavior almost immediately. This helps resolve some of the puzzles raised by thought experiments, like Schrödinger's cat. The cat doesn't remain in a superposition of alive and dead for long, because it is heavily entangled with its surroundings, the air in the box, the molecules in its body, and even the thermal radiation around it. Decoherence ensures that only one outcome becomes visible, even if the underlying quantum state is still complicated. In quantum computing, decoherence is a major challenge. Quantum computers rely on superpositions and entanglement to perform calculations. But if the system decoheres too quickly, the quantum information is lost. That's why quantum computers must be carefully isolated from their environment, and why researchers work so hard to correct for errors caused by decoherence. It's important to understand that decoherence is not the same as randomness. It doesn't make quantum systems unpredictable. Instead, it explains why the probabilistic nature of quantum mechanics gives rise to the definite, classical world we observe. It provides the link between quantum rules and classical outcomes. Quantum decoherence doesn't solve all the mysteries of measurement. It doesn't tell us exactly when a quantum system becomes a classical one, but it gives us a framework for understanding why the quantum world appears hidden, why we don't see particles in two places at once, why the weirdness of superposition fades as systems grow larger and more connected to their surroundings. In that sense, decoherence is not a breakdown of quantum mechanics. It is quantum mechanics at work, showing us how the familiar world of solid objects and definite outcomes emerges from the uncertain probabilistic world underneath. Special relativity. Special relativity is the theory that changed our understanding of space, time, and motion. Proposed by Albert Einstein in 1905, it replaced the old idea that space and time are fixed and absolute. Instead, it showed that they are flexible and connected, depending on how fast you're moving. At the heart of special relativity is a simple observation. The speed of light is the same for all observers, no matter how fast they are moving. Whether you are standing still or flying in a spaceship, if you measure the speed of light, you will always get the same number, about 299,792,458 meters per second. This idea sounds innocent at first, but it has huge consequences. To keep the speed of light constant, space and time themselves must adjust. Time can slow down, lengths can shrink, and events that seem simultaneous to one observer may not be simultaneous to another. One of the most famous effects predicted by special relativity is time dilation. If you are moving very fast, close to the speed of light, time passes more slowly for you compared to someone who is standing still. This isn't just theory. It has been measured in particle accelerators, where fast-moving particles live longer than they would at rest. It's also been tested with atomic clocks on airplanes. The faster you move, the more slowly your clock ticks. Another consequence is length contraction. If you are traveling at high speed, objects in the direction of motion appear shorter. From your perspective, the space you're moving through becomes compressed. This effect becomes noticeable only at speeds approaching the speed of light, but it is a real and measurable feature of the universe. Then, there's the idea of relativity, of simultaneity. Events that appear to happen at the same time for one observer may happen at different times for someone else moving at a different speed. There is no single universal now. What one observer sees as two lightning strikes happening at once, another might see as one happening before the other. This means that time is not a global clock. It's personal, dependent on your frame of reference. Special relativity also changed the way we think about mass and energy. Einstein's famous equation, E equals mc squared, tells us that mass and energy are two forms of the same thing. A small amount of mass contains a tremendous amount of energy. This principle explains how the sun shines, how nuclear reactions work, and why energy and mass can be converted into each other under the right conditions. Importantly, special relativity applies only to objects moving at constant speeds, in straight lines, and not accelerating. That's why it's called special. It doesn't include gravity or curved space-time. Those effects are explained by general relativity, which Einstein developed later. But even on its own, special relativity has had a huge impact on physics, technology, and our understanding of reality. You don't need to travel at light speed to see its effects. Global Positioning System satellites, or GPS, must account for special relativity to keep their timing accurate. Without correcting for time dilation, GPS devices would quickly become inaccurate by several kilometers per day. The theory is not just elegant, it's practical. One way to picture special relativity is to think of space and time as a single fabric called space-time. Instead of treating space and time as separate, special relativity shows they are part of a single, four-dimensional reality. When you move through space, you are also moving through time, and how fast you move through one affects how fast you experience the other. Special relativity replaced the old Newtonian view of the universe with a new picture, one where the laws of physics are the same for all observers, but measurements of space and time depend on how fast you're moving. It showed that space and time are not rigid backgrounds. They are dynamic and responsive, shaped by motion and perspective. What began as a theory of motion turned into a revolution in how we understand the universe. Special relativity showed that time is not absolute, distances are not fixed, and energy and mass are deeply connected. It remains one of the most beautiful and well-tested theories in physics. Time dilation. Time dilation is one of the most fascinating and counterintuitive consequences of Einstein's theory of special relativity. It tells us that time does not pass at the same rate for everyone. Instead, how fast time flows depends on how fast you are moving. According to special relativity, the faster you travel relative to someone else, the more slowly time passes for you compared to them. This is not a perception or an illusion. It's a real effect, confirmed by both theory and experiment. Clocks moving at high speed literally tick more slowly when viewed from a stationary frame. To understand why this happens, we need to go back to the basic principle of special relativity. The speed of light is the same for all observers, no matter how fast they are moving. If the speed of light is fixed, then space and time must adjust to make that work. One of those adjustments is time dilation. Let's consider a simple example. Imagine a spaceship moving very fast through space. Inside the ship, a beam of light bounces up and down between two mirrors. To someone on the ship, the light beam travels vertically, straight up and down. But to someone watching from outside, the ship is moving. So the light beam traces a diagonal path, covering more distance, because the speed of light must remain constant for both observers. The only way to make the math work is if time slows down on the ship. That way, the light still moves at the same speed, even though it's taking a longer path. This slowing down of time is time dilation. The effect becomes more dramatic the closer you get to the speed of light. At everyday speeds, the change is so small that it's unnoticeable. But as your velocity approaches the speed of light, time slows down significantly. In fact, if you could travel at 99.99% of the speed of light, 1 second for you might be several minutes, or even hours for someone at rest. This leads to the famous twin paradox. Imagine two twins. One stays on Earth, while the other travels on a high-speed journey into space, then returns. According to special relativity, the traveling twin experiences less time during the trip. When they return, they are younger than the twin who stayed on Earth. It's not a trick, it's a consequence of how motion affects time. Time dilation isn't just a thought experiment, it has been measured in many ways. For example, particles called muons are created high in Earth's atmosphere when cosmic rays hit. Muons are unstable and decay quickly, too quickly to reach the surface of the Earth if their clocks tick normally. But because they are moving near the speed of light, time slows down for them. This allows many muons to survive long enough to be detected on the ground. Their extended lifetime is direct evidence of time dilation. Another real-world application is the Global Positioning System. GPS satellites orbit the Earth at high speeds. If time dilation were not accounted for, their onboard clocks would drift out of sync with clocks on the ground, and GPS locations would quickly become inaccurate. Engineers must correct for both special relativity, due to their speed, and general relativity, due to their position in Earth's gravitational field. One way to think about time dilation is to imagine that everyone carries their own clock, and that clock is influenced by how they move through space. The faster you move through space, the slower you move through time. This is because space and time are not separate. They are part of a single fabric called space-time. Motion through one affects how you experience the other. Time dilation teaches us that time is not absolute. It is relative, tied to the observer's frame of reference. Two people moving differently through space can genuinely disagree on how much time has passed, and both can be correct within their own context. It's a reminder that our intuition, shaped by everyday experience, doesn't always match the deeper reality uncovered by physics. At high speeds, the universe behaves in ways that seem strange, but are entirely consistent with the principles of relativity. Length contraction. Length contraction is another key prediction of Einstein's special relativity, and it describes how objects appear shorter in the direction of motion when they're moving close to the speed of light. Just like time dilation shows that time slows down for moving observers, length contraction shows that distances shrink. This effect is not about illusion or distortion. It is a real, physical consequence of how space and time behave at high speeds. Unlike time dilation, it arises from the fact that the speed of light is constant for all observers, no matter how fast they are moving. To see how this works, imagine a spaceship traveling past Earth at a significant fraction of the speed of light. To someone on Earth, the ship appears compressed along its direction of motion. It's shorter than it would be if it were sitting still, but to the person on the ship, nothing appears different. The ship feels normal in size. Instead, from their point of view, it is Earth that appears contracted. This asymmetry happens because space and time are not separate in special relativity. They are part of a unified structure called space-time. When you move through space, your experience of space and time changes. The faster you move, the more you see lengths contract and time slow down in the frame you are moving relative to. The equation that describes length contraction is simple. The contracted length equals the original length multiplied by the square root of 1 minus v squared divided by c squared, where v is the velocity of the object, and c is the speed of light. As the object's velocity increases, the contracted length becomes smaller and smaller. At the speed of light, the length would contract to 0. This tells us that an object's length depends on the frame of reference. In its own rest frame, the object keeps its original length, but to an outside observer moving relative to the object, it appears shorter. This effect only becomes noticeable at very high speeds, close to the speed of light. At everyday speeds, the contraction is far too small to detect. Let's use an analogy. Imagine you are driving down a long road at normal highway speeds. You look out the window, and the trees and poles seem to fly by, but the distance between them doesn't change. Now imagine accelerating to nearly the speed of light. To someone watching from the side of the road, your car appears squashed in the direction it's moving. It's shorter than normal, but to you, everything inside the car feels normal. Instead, it's the road outside that appears compressed. This idea might seem strange, but it's not optional. It's a necessary part of keeping the speed of light constant for all observers. If lengths didn't contract, and if time didn't slow down, the laws of physics wouldn't work the same in different frames. Relativity requires these changes to preserve consistency. Like time dilation, length contraction has been confirmed by experiments. When high-energy particles move through the atmosphere, the distances they travel appear shorter from their perspective. This contributes to their ability to reach detectors on the ground before decaying. The contraction of space makes the journey quicker from the particle's point of view. These relativistic effects also play a role in particle accelerators, where subatomic particles are pushed to near light speed. The distances they travel, the times they exist, and even their masses must all be calculated using the rules of special relativity, including length contraction. Length contraction reveals that space, like time, is not absolute. It depends on how fast you're moving. What one observer measures as a fixed length, another may measure as a shorter one, and both will be right in their own frames of reference. Overs. This is not just a mathematical curiosity. It's a fundamental shift in how we understand motion, space, and reality itself. In the realm of high speeds, space and time are flexible, and length contraction is a vivid demonstration of that flexibility. General relativity. General relativity is Einstein's theory of gravity. It extends the ideas of special relativity and presents a completely new way of thinking about what gravity is and how it works. Instead of describing gravity as a force pulling objects together, general relativity describes it as the curvature of space-time caused by mass and energy. The key idea is simple but powerful. Matter tells space-time how to curve, and curved space-time tells matter how to move. In Newton's view, gravity is a force that acts at a distance. The Earth pulls on the Moon, and the Moon pulls back on the Earth. But Einstein realized that this description had problems, especially when combined with the constant speed of light and the principles of special relativity. It didn't explain how gravitational effects travel or how they interact with the geometry of space itself. So he proposed something radical. Instead of treating space and time as a static stage where objects move, he treated them as dynamic and flexible. Mass and energy warp the fabric of space-time, and this curvature affects how objects move. What we experience as gravity is simply the motion of objects following curved paths through this distorted space-time. You can visualize it by imagining a rubber sheet. If you place a heavy ball in the center, it creates a dent in the sheet. Now roll a smaller ball nearby. It will spiral toward the larger ball, not because they are pulling on each other directly, but because the smaller ball is following the curved surface created by the larger one. That's a rough analogy for how general relativity works. This theory leads to several important predictions, many of which have been confirmed by observation. One of them is that light doesn't travel in a straight line when it passes near a massive object. Instead, it bends slightly, following the curve of space-time. This bending was first observed during a solar eclipse in 1919, when starlight passing near the Sun was seen to shift. It was the first major confirmation of general relativity, and it made Einstein a global figure overnight. Another prediction is the slowing of time in strong gravitational fields. This is known as gravitational time dilation. Near a massive object, such as a planet or a black hole, time passes more slowly compared to regions farther away. This effect has been confirmed by precision clocks on Earth and in orbit, and it must be taken into account for systems like GPS to remain accurate. General relativity also predicted the existence of black holes, regions of space where the curvature becomes so extreme that not even light can escape. The idea sounded speculative at first, but black holes have since been detected through their effects on nearby matter and through gravitational waves emitted when they collide. In 2015, a century after Einstein proposed general relativity, scientists detected gravitational waves for the first time. These are ripples in space-time itself, caused by massive objects like black holes or neutron stars orbiting and merging. They travel outward at the speed of light and stretch and squeeze space as they pass. Their discovery marked a new era in astronomy, allowing us to observe cosmic events that were previously invisible. Mathematically, general relativity is described by a set of equations called the Einstein field equations. These equations relate the curvature of space-time to the distribution of mass and energy. They are complex and difficult to solve, but they have provided stunningly accurate predictions, from the expansion of the universe to the behavior of stars and galaxies. One of the most beautiful aspects of general relativity is how it unifies space, time, and gravity into a single framework. It shows that gravity is not a mysterious force. It is geometry. It is the shape of space-time itself. This theory has passed every experimental test to date, from bending starlight to shifting planetary orbits, from slowing time near black holes to guiding spacecraft across the solar system. General relativity continues to shape our understanding of the universe. It is one of the greatest achievements in physics, a theory that explains the motion of planets, the dynamics of stars, and the structure of the cosmos. And yet, it also points toward new mysteries, like what happens at the center of a black hole, or how gravity works at quantum scales. Einstein's theory reshaped reality. It taught us that space and time are not passive backgrounds, but dynamic participants in the story of the universe. Space-time. Space-time is the foundational concept that unifies space and time into a single, four-dimensional fabric. Instead of treating space and time as separate and independent, modern physics, starting with Einstein's theory of relativity, shows that they are deeply connected. They form a single entity that shapes everything we know about motion, gravity, and the structure of the universe. In our everyday experience, we tend to think of space as three-dimensional. You can move left and right, forward and backward, up and down. Time, on the other hand, seems like something entirely different, something that flows forward at a constant pace. But according to the theory of relativity, that separation is artificial. Space and time are not distinct. They are intertwined. This union is known as space-time. It has four dimensions, three of space and one of time. Every event in the universe, every action, every movement, every flash of light occurs at a point in this four-dimensional structure. That point is called an event, and it has a position in both space and time. To understand why this matters, imagine two observers watching the same event, say, a flash of lightning. If the observers are moving at different speeds or in different directions, they may disagree on when or where the lightning occurred. One might say, it happened a little earlier, or a little farther away. Both are correct in their own frame of reference. That's because, in space-time, coordinates shift depending on your motion. This relativity of space and time becomes crucial at high speeds or in strong gravitational fields. As objects move faster, time slows down for them, and distances shrink along the direction of motion. In curved spacetime, caused by gravity, the shortest path between 2 points may not be a straight line. Instead, it curves. That's why planets orbit stars. They are not being pulled by an invisible force. They are simply following curved paths through spacetime. Einstein's general theory of relativity describes how mass and energy curve spacetime. The more massive an object is, the more it distorts the spacetime around it. That curvature affects the motion of other objects, guiding them along specific paths. This is what we experience as gravity. One way to picture this is with a flexible rubber sheet. If you place a heavy ball in the center, it creates a dent. Roll a smaller ball nearby, and it spirals inward, not because of a direct pull, but because the surface itself is curved. That's an analogy for how massive objects bend space-time and how smaller objects respond. But space-time isn't just about big cosmic motions. It affects things we rely on every day. The timing of GPS satellites, the orbit of the moon, the bending of starlight around the sun, all are shaped by space-time geometry. Even the flow of time changes depending on where you are and how fast you're moving. Mathematically, space-time is described using the tools of geometry and calculus. Each point is labeled with 4 coordinates, 3 for space, 1 for time. The structure of space-time determines how those points relate, how particles move, and how light travels. It is the stage on which the universe plays out, but it is not passive. It responds to mass and energy and evolves with them. And yet, despite its complexity, space-time is also elegant. It gives us a unified picture of reality. Instead of treating time as a separate ticking clock, it becomes a direction, just like up or forward. The passage of time is simply movement through this 4-dimensional landscape. Understanding space-time changes the way we see the universe. It helps explain why light bends, why time runs differently on mountaintops than at sea level, and why clocks on fast-moving spacecraft tick more slowly. It connects motion, gravity, and the shape of the cosmos in a single framework. Space-time is not just a background for physical events. It is an active participant in the dynamics of the universe. It curves, stretches, ripples, and evolves. It's the fabric of reality itself, and the more we study it, the more it reveals about the nature of existence. Gravitational lensing. Gravitational lensing is a phenomenon that occurs when light from a distant object, like a star or a galaxy, bends as it passes near a massive object, such as another galaxy or a black hole. This bending is caused by the curvature of spacetime, as described by Einstein's general relativity. The result is that the massive object acts like a lens, warping and magnifying the light behind it. In classical physics, light travels in straight lines, but in general relativity, straight lines don't always look straight. When space-time itself is curved by the presence of mass or energy, light follows the shape of that curvature. So what we observe as a bent path is actually light moving in a straight line through a curved space-time. Imagine placing a heavy ball on a rubber sheet and rolling a marble nearby. The marble curves around the dent created by the heavy ball. In a similar way, light curves around massive objects, not because it is attracted by a force, but because the space it travels through is warped. Gravitational lensing was one of the first major confirmations of general relativity. In 1919, during a solar eclipse, astronomers observed that light from distant stars was slightly shifted as it passed near the sun. The stars appeared in slightly different positions than expected. This confirmed Einstein's prediction and showed that light, though massless, is affected by gravity. There are 3 main types of gravitational lensing. The first is strong lensing. Where the distortion is large enough to produce dramatic visual effects, multiple images of the same object, bright arcs of light, or even complete rings. These rings, called Einstein rings, occur when the source, the lens, and the observer are perfectly aligned. The second type is weak lensing. In this case, The bending of light is subtle. Instead of multiple images, we see small distortions in the shapes of galaxies. By studying these patterns across the sky, astronomers can map the distribution of dark matter, which doesn't emit light, but does bend space-time. The third type is microlensing. This happens when a relatively small object, like a star or even a planet, briefly magnifies the light of a more distant background star. Microlensing has been used to detect planets outside our solar system, including ones that would be impossible to see with ordinary telescopes. Gravitational lensing is like nature's own magnifying glass. It allows us to see objects that are too faint, too far, or otherwise hidden. Some of the most distant galaxies ever observed were made visible only because of the magnifying power of lensing. This effect also provides a way to measure the mass of galaxies and clusters, even when much of that mass is invisible. By observing how much the background light is bent, astronomers can calculate how much matter must be present to cause the distortion. This technique has revealed that most of the matter in the universe is dark. It does not emit or reflect light, but it does bend space. In some cases, gravitational lensing even lets us look back in time, because light from distant galaxies takes billions of years to reach us. We're seeing those galaxies as they were long ago. When lensing amplifies that light, we can study the early universe in much greater detail. From a technical standpoint, lensing is governed by the Einstein field equations, which relate the curvature of space-time to the mass and energy causing it. The light path is calculated using what are called geodesics, the shortest possible routes through curved space-time. These are not straight lines in the Euclidean sense, but they are the paths that light naturally follows. Gravitational lensing is not just a curious effect. It's a practical tool for studying the universe. It helps us detect planets, understand galaxy formation, measure dark matter, and probe the structure of the cosmos on the larger scales. And perhaps most profoundly, it reminds us that light is not immune to gravity. Even the fastest thing in the universe, moving at the speed of light, must obey the curvature of space-time. In that sense, gravitational lensing is a visible signature of the invisible shape of space. Black holes. Black holes are among the most mysterious and extreme objects in the universe. They are regions of space where gravity becomes so intense that nothing, not even light, can escape. They are not simply very dense stars. They are what happens when space-time itself is pushed to its breaking point. A black hole begins its life as a massive star toward the end of its life. After it has burned through its nuclear fuel, the star can no longer support itself against the force of gravity. It collapses under its own weight. If the remaining mass is large enough, the collapse doesn't stop. The core shrinks smaller and smaller until it becomes a singularity, a point of infinite density where the known laws of physics no longer apply. Surrounding the singularity is the event horizon. This is the boundary beyond which nothing can return. It's not a physical surface, but a one-way edge in space. Once something crosses the event horizon, it cannot escape, not because it lacks energy, but because the structure of space-time is so distorted that all paths lead inward. To an outside observer, anything falling in appears to slow down as it approaches the event horizon, never quite crossing it. But from the perspective of the falling object, the descent is inevitable and quick. Black holes can vary in size. Some are a few times more massive than the Sun. These are called stellar mass black holes. Others are millions or even billions of times more massive, sitting at the centers of galaxies. These are supermassive black holes, and they likely formed in the early universe, growing over time as they consumed matter and merged with other black holes. There is also growing evidence for intermediate mass black holes, and even the possibility of primordial black holes, tiny black holes, that might have formed in the first moments after the Big Bang. Despite their reputation as cosmic vacuum cleaners, black holes do not suck in everything around them. If the Sun were replaced with a black hole of the same mass, Earth would continue orbiting it in the same path. What makes black holes so powerful is not their pull, but the fact that they compress so much mass into such a tiny region, creating extreme curvature in space-time. One of the most fascinating discoveries in recent years was the first direct image of a black hole's shadow captured by the Event Horizon Telescope in 2019. It showed the glowing ring of hot gas orbiting the black hole in the galaxy. The dark center was not the black hole itself, but the silhouette of the event horizon, proof that these objects are real and can be observed. Black holes also emit gravitational waves when they collide.
These are ripples in space-time that travel across the universe. In 2015, the LIGO experiment detected gravitational waves from a pair of merging black holes. It was the first direct confirmation of Einstein's prediction and opened a new window into the universe.
But black holes are not just a test of gravity. They challenge our understanding of information and quantum mechanics. According to general relativity, anything that falls into a black hole is lost forever. But according to quantum theory, information cannot be destroyed. This leads to the black hole information paradox. One of the biggest unresolved puzzles in physics. Stephen Hawking added another twist in the 1970s when he showed that black holes are not entirely black. Due to quantum effects near the event horizon, they can emit radiation, now called Hawking radiation. Over time, this causes black holes to slowly evaporate. For large black holes, this process is extremely slow, but for tiny ones, it could be significant. So black holes are not just strange, they're central to our search for a deeper understanding of reality. They sit at the intersection of gravity, quantum mechanics, thermodynamics, and cosmology. They are not cosmic monsters. They are natural consequences of the laws of physics pushed to their limits. They test the edges of our theories and push us to ask better questions about space, time, and the fate of information. Black holes are where the universe reveals its deepest secrets and where our current understanding begins to fall apart. Gravitational waves. Gravitational waves are ripples in the fabric of space-time. They are produced by the acceleration of massive objects, especially during violent cosmic events like the collision of black holes or the explosion of massive stars. These waves travel outward from their source at the speed of light, stretching and squeezing space as they pass through it. The idea of gravitational waves comes directly from Einstein's theory of general relativity. In that theory, gravity is not a force in the traditional sense, but the curvature of space-time caused by mass and energy. When that mass moves in a dynamic, non-symmetric way, like two black holes orbiting each other, it can create disturbances in space-time that radiate outward. These disturbances are what we call gravitational waves. For decades, gravitational waves were only a theoretical prediction. No one had ever detected them directly. But that changed in 2015, when scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, announced the first confirmed detection of gravitational waves. The signal came from two black holes spiraling into each other, more than 1 billion light-years away. Their collision sent a tiny ripple through space-time that reached Earth, where LIGO's incredibly sensitive detectors were able to record it. Detecting gravitational waves is extremely difficult because the distortions they cause are incredibly small, many times smaller than the width of a proton. LIGO and its European counterpart, Virgo, use laser interferometry to measure these minuscule changes. Two long arms, with mirrors at the ends, are used to create a stable laser path. When a gravitational wave passes, it slightly changes the length of one arm compared to the other. That change, though unimaginably tiny, is enough to be detected. The discovery of gravitational waves was not just a triumph of engineering. It opened a completely new way of observing the universe. Until now, almost all astronomy relied on light, visible light, radio waves, X-rays, and other parts of the electromagnetic spectrum. But gravitational waves are different. They pass through matter almost completely undisturbed. This means they carry information about regions of space that light can't reach, like the interiors of black hole collisions or the very early universe. Since that first detection, Leda and Virgo have observed dozens of gravitational wave events. Most come from merging black holes, but others involve neutron stars, the incredibly dense remnants of exploded stars. When two neutron stars collide, they produce gravitational waves and also a flash of light. Observing both signals allows scientists to study the event in more detail, combining information from different messengers. This is called multi-messenger astronomy. Gravitational waves also provide a way to test general relativity in the most extreme conditions. So far, Einstein's predictions have held up perfectly. The waves travel at the speed of light. Their strength and shape match the models. But future observations might reveal subtle differences, clues that could point toward new physics. There is also hope that gravitational waves could help us understand the early universe. Right after the Big Bang, space-time may have undergone rapid inflation, producing gravitational waves that are still echoing through the cosmos. These primordial waves are incredibly faint, but if we can detect them, they might tell us what happened in the first fraction of a second after time began. Gravitational waves are not science fiction. They are real, measurable distortions in the structure of space itself. They confirm that space-time is not static. It can bend, stretch, and ripple, and they prove that the universe is dynamic, filled with motion, collisions, and energy flows that we are only beginning to observe. In a way, gravitational waves are the universe speaking in a new voice, a deep, low hum that tells the story of massive objects in motion. And by listening carefully, we are now able to hear that voice for the first time. The Big Bang. Imagine a time when there was nothing, no stars, no planets, no matter as we know it, and even no space or time. It's difficult to wrap our minds around such a concept, isn't it? Yet this is where our story begins, at a point we refer to as the Big Bang. But the term Big Bang might be misleading. It wasn't an explosion in the traditional sense. Rather, it was the beginning of the universe's expansion, creating both space and time in the process. Think of a balloon, initially deflated and tightly crumpled. As you start blowing air into it, the surface of the balloon expands in every direction. Similarly, the fabric of space itself expanded from a highly dense and hot singularity. This expansion continues to this day, ever inflating the cosmic balloon. But remember, what was actually inflating was not a pre-existing space. Space itself was being created. In the moments directly following the Big Bang, the universe was unimaginably hot and dense. The fundamental forces of nature as we know them, gravity, electromagnetism, and the strong and weak nuclear forces were unified. Within fractions of a second, this superforce began to break apart, much like ice melting into water. As the universe continued to expand and cool, these forces decoupled into the familiar forms we recognize today. During this infancy of the universe, a peculiar phenomenon called cosmic inflation may have occurred. This brief period, lasting for just an infinitesimal fraction of a second, allowed the universe to expand exponentially. Imagine a small balloon suddenly swelling to the size of a giant beach ball, almost instantaneously. Cosmic inflation helped explain why different regions of the universe appear remarkably similar, and also ironed out any initial irregularities, leaving the cosmos relatively uniform in all directions. As the universe cooled, it transitioned from an opaque, glowing mass into a transparent state where light could finally travel freely. This event is known as recombination, and it occurred about 380,000 years after the Big Bang, remarkably soon in cosmic terms. At this point, electrons combined with protons to form neutral hydrogen atoms, marking the first time light could move about unimpeded. Today, we observe this ancient afterglow as cosmic microwave background radiation, a snapshot of the early universe that tells us much about our origins. Now, let's delve into time itself. Before the Big Bang, asking what happened before is not a valid question, because time, as we understand it, did not exist. In essence, time began ticking from the moment of the Big Bang. The concept of before the Big Bang has no real meaning. similar to asking for a location north of the North Pole. As humans, our daily lives revolve around the ticking hands of a clock, from seconds to minutes to years. Yet, on a cosmic scale, time operates rather differently. You might liken it to watching a movie in super slow motion, where changes happen over millions and even billions of years. The birth of stars, their life cycles, and their eventual demise are all chapters in the story of cosmic time, stories that we can read and understand through observations and scientific endeavor. It is awe-inspiring to realize that everything we see, all that we know, emerged from such humble origins. The stars, planets, galaxies, and more, all formed through the gradual clumping and cooling of matter under the influence of gravity. The building blocks born from that initial cauldron of energy expanded and formed everything, from the tiniest grains of sand to the mightiest supermassive black holes. This expansion of space and the flow of time continue, driving the dance of galaxies across billions of light years. It raises profound questions about the ultimate fate of the universe. Will the expansion go on indefinitely, or will it slow and reverse, culminating in a big crunch? Or perhaps, will it reach a cosmic standstill? While these questions linger, they serve as poignant reminders of the vast and dynamic universe we inhabit. A universe whose story began with the birth of time and space. Cosmic inflation. Imagine you're at the start of a thrilling race, and suddenly, the track you're on stretches at an unimaginable speed, leaving everything else behind in a flurry of motion. This is somewhat analogous to what happened during a very early phase of our universe known as cosmic inflation. In a tiny fraction of a second, the universe expanded faster than the speed of light, transforming from a minuscule point to something vast and expansive. Cosmic inflation is believed to have occurred just after the Big Bang, around 10 to the negative 36 seconds to 10 to the negative 32 seconds after time began. These numbers are incredibly small, just a flash in the cosmic timeline, yet these moments were crucial. During this brief period, the universe experienced exponential growth, increasing in size by at least a factor of 10 to the 26th power. Imagine blowing up a balloon to the size of a room in less than a heartbeat. But why did inflation happen, and what does it tell us about the universe today? The key idea is tied to a peculiar type of energy known as the inflaton field. Just like a field of corn has energy stored in every ear of corn, the early universe housed this inflaton field. The energy in this field caused the universe to expand suddenly and dramatically. Now let's dive into why this rapid growth was so important. Inflation helps solve a few cosmic puzzles, like why the universe appears so uniform and strangely smooth. You might notice that the distant universe looks pretty much the same no matter where you look. This uniformity, or isotropy, is puzzling because no signals could have traveled across the vast distances to give the universe enough time to even itself out before inflation. However, by stretching everything quickly from a tiny uniform region, inflation explains why distant parts of the universe look similar today. Another mystery inflation resolves is why the universe is nearly flat. In a geometric sense, a flat universe means that parallel lines, if extended infinitely, would never meet. Before inflation, the curvature of space, be it closed like a sphere or open like a saddle, was more pronounced. But inflating a curved space-time so rapidly is like taking a tiny piece of a ball and expanding it until it resembles a flat plane. The more you stretch, the flatter it appears. Inflation also has an effect on the microscopic scale. Quantum fluctuations, the tiny random changes that happen at the subatomic level, were dramatically magnified during inflation. Think of cosmic inflation as a copier that enlarges these quantum ripples, turning them into the seeds for all future cosmic structures like galaxies, stars, and planets. These magnified fluctuations became the blueprint for the universe's large-scale structure seen today in galaxy distribution. Thanks to these nuances, cosmic inflation is a pivotal part of current cosmological models. But keep in mind, while inflation is a compelling explanation, it's still a theory. Astronomers are continually seeking evidence to support it. One of the most exciting searches involves the cosmic microwave background radiation, often dubbed the afterglow of the Big Bang. Scientists are on the lookout for specific patterns, known as B-mode polarization, in this background light that could point directly to the fingerprints of cosmic inflation. To appreciate inflation is to imagine a time when the cosmos was still in its infancy and undergoing changes that define the universe we observe today. It's humbling, in a way, to realize that the stars, galaxies, and cosmic structures floating in the vastness of space can trace their origins back to this rapid growth spurt. In just a fraction of a second, inflation set the stage for everything that followed, shaping a universe that, billions of years later, we have come to explore and understand. Cosmic microwave background. Imagine a time machine, one that doesn't take you to the future or far into the reaches of the cosmos, but all the way back to the beginning, the very beginning, to a time when the universe was only a hot, dense fog of particles. In this place, we find the cosmic microwave background, or CMB, the universe's first light. Picture it like this. When you look up at the night sky, you see stars and galaxies that twinkle like 1,000 eyes staring back. But these are only the recent creations. Relatively speaking, before the first stars, before the first galaxies, there was light, an all-encompassing glow that filled the cosmos. This light gives us the earliest snapshot of the universe, a mere 380,000 years after the Big Bang, which might seem like a while, until you compare it to the universe's current age of about 13.8 billion years. Now, what is this cosmic glow, this relic from a time just after everything we know came into being? The universe began in a hot and dense state, almost like an immense, boiling soup of particles. Atoms, as we know them, couldn't exist yet, because they were continually hammered by high-energy photons, which are particles of light. These photons were so energetic that they would knock electrons off newly formed atoms, preventing stable matter from forming. As the universe expanded, it cooled down. This is much like steam cooling to form water droplets. Eventually, the particles slowed down enough to combine into simple atoms, mainly hydrogen and helium. This transformative moment is called recombination, and it was groundbreaking because it allowed photons to travel freely for the first time. Before this, the universe was opaque. Photons were constantly scattered by electrons in a dense plasma, rendering any light unable to travel far. With recombination, the universe became transparent, and those first free streams of light began their journey, echoing across the cosmos. These primordial photons are what we now observe as the cosmic microwave background, faint and ever-present, whispering stories from the birth of the cosmos. The CMB is remarkably uniform in every direction we observe, but tiny variations do exist. These variations are crucial because they later led to the formation of all the cosmic structures we see today, from stars to galaxies. Detecting this ancient light took ingenuity. It was first discovered unintentionally in 1964 by Arno Penzias and Robert Wilson, who were experimenting with a radio antenna. They stumbled upon a persistent noise, a hum that came no matter where they pointed their device. This hum wasn't coming from the Earth or our galaxy, but from the universe itself. They realized they had found the remnant of the Big Bang, now redshifted into the microwave part of the spectrum due to the immense stretching of the universe. Think of it like an echo. If you shout your name into a canyon, your voice reverberates back, a bit softer and distorted with each bounce. The CMB is the echo of the Big Bang, weakened and stretched by the expansion of space-time. The CMB's discovery has been pivotal. It offers one of the strongest pieces of evidence supporting the Big Bang theory. Furthermore, by studying it, scientists can learn about the universe's fundamental properties, such as its age, its rate of expansion, and its fate. Ever since that fateful discovery, we've built sophisticated instruments like the COBE, WMAP, and Planck satellites to study the CMB in exquisite detail. These observations allow us to map the early universe with unprecedented precision. In this cosmic glow, we see the seeds of galaxies and the patterns of matter that would shape the universe's vastness. It's like a cosmic blueprint, etched in the faint glow of microwaves, offering us a window into the vital forces that have driven the universe's evolution. So, when you gaze into the night sky and let the darkness envelop you, remember that unseen and ancient, the universe's first light still hums quietly, connecting us to the dawn of everything we know. Dark matter. In the vast tapestry of the cosmos, filled with countless stars and galaxies, there lies an enigmatic presence, a force unseen, yet profoundly impactful. It's called dark matter. Imagine wandering through a vast silent forest at night. You can't see the wind, but you can feel it rustling the leaves and hear it whistling through the branches. Dark matter is similar to this invisible wind, exerting influence without ever showing its face. The complete story of dark matter begins with something as innocuous as the rotation of galaxies. When astronomers like Vera Rubin observed spiral galaxies, they expected to find that stars on the outer edges revolved around the center at slower speeds, much like the outer planets in our solar system, orbit slower than those closer to the sun. However, what they uncovered was astonishing. The stars on the outskirts were moving just as swiftly as those near the core. This was confounding because the visible mass of the galaxy, all the stars, gas, and dust, couldn't account for such high speeds. It's as if there were an unseen gravitational glue holding these stars in place, an invisible scaffolding. Now, you might be wondering how much of this invisible stuff there actually is. The surprising answer is that dark matter makes up about 27% of the universe's content, with visible matter composing merely about 5%. The rest is dark energy, but that's a story for another time. To put that in perspective, if the universe were a giant iceberg, all the stars and planets we can see would be just the tip sticking out above the water, with dark matter forming a significant chunk below the surface. Many hypotheses have attempted to explain what dark matter could be. Initially, scientists pondered whether it could be made up of regular matter that's just hard to see, like dim stars or rogue planets. But they eventually ruled this out. What became clear is that dark matter doesn't interact with light in the way normal matter does. It's invisible, not just because it's in the dark, but because it doesn't emit, absorb, or reflect light. This leads us into the realm of the so-called WIMPs, or weakly interacting massive particles, one of the leading candidates for dark matter. If the universe were a grand masquerade ball, WIMPs would be the elusive guests who move through the crowd unseen and mostly unfelt. They barely interact with ordinary matter, slipping through barriers that would stop other particles in their tracks. Despite its elusiveness, scientists around the world have crafted ingenious ways to study dark matter. They use sensitive underground detectors to catch the rare moment when a WIMP might interact with a regular particle. Observatories are tuned to detect gravitational fluctuations, the subtle clumping of galaxies under dark matter's influence. Through these methods, they've started to piece together the shadowy puzzle. Dark matter also plays a vital role in the formation of the universe itself. Picture the early universe as a bubbling pot of soup. Without dark matter, the soup would have simply simmered without coming together into anything solid. Dark matter acted like an unseen stirrer, gathering gas and dust to form stars and galaxies, shaping the universe over billions of years. In the cosmic story, dark matter is a silent character, essential yet mysterious. It's a testament to how much remains to be explored, a reminder of our continuing quest to understand the universe's deepest secrets. As we peer into the night sky, filled with visible stars, it's humbling to think that what we see is just the surface of a grander realm, shaped largely by forces that remain beyond our sight and touch. The mystery of dark matter continues to entice scientists, like a key unlocking new chapters in the vast book of the cosmos. In the vast expanse of the universe, a mysterious force is at play, tugging at the very fabric of space itself. This force, known as dark energy, is responsible for one of the most astonishing discoveries in modern astrophysics, the accelerated expansion of the universe. To understand dark energy, imagine the universe as an enormous stretchy fabric, like a trampoline. Objects like galaxies and stars sit atop this fabric, warping it with their gravitational pull. For a long time, scientists thought that the fabric, space itself, was being pulled inward, or at least slowly decaying, due to the attractive force of gravity. However, in the late 1990s, astronomers studying distant supernovae, which are colossal explosions marking the death of certain types of stars, discovered something unexpected. Instead of slowing down, these far-off cosmic milestones were moving away from us more rapidly than anyone had predicted. This implied that the universe wasn't just expanding, it was accelerating in its expansion. Picture a car gaining speed as it moves down an incline. Except, in this case, there's no incline, just the invisible force of dark energy pushing it ever outward. Dark energy makes up about 68% of the total energy content of the universe, dwarfing all the stars, galaxies, and planets combined. Yet, it's exceedingly elusive. Unlike matter, which clumps together to form the celestial objects we see, dark energy is diffused. It's spread evenly throughout the cosmos, acting uniformly wherever space exists. You might think of it as the gentle but relentless push that fills the voids of space. One popular theory about dark energy is that it could be a property of space itself, tied to what physicists call the cosmological constant, proposed originally by Albert Einstein as a fudge factor to his equations of general relativity. The cosmological constant describes a vacuum energy inherent to space. Even in the absence of matter, space would have this intrinsic energy that would exert a repulsive force, countering the pull of gravity. Another intriguing idea is that dark energy might be linked to a new kind of dynamical energy field that permeates space, sometimes referred to as quintessence. Quintessence, if it exists, would change its strength over time and space. Unlike the constant push described by the cosmological constant, to conjure a sense of this, envision a pulsing field that ebbs and flows, subtly influencing the universe's expansion rate. Despite these theories, dark energy remains one of the biggest puzzles in modern science, rooted as much in imagination as in observation. To probe its secrets, scientists employ a range of observational tools. They measure the cosmic microwave background radiation, analyze the distribution of galaxies, and use gravitational lensing, where the path of light from distant objects bends around massive structures, to study the effects of this enigmatic force. These observations continuously test our understanding of dark energy's nature. Yet, defining what dark energy tested poses profound challenges, requiring us to reconcile it with the basic principles of physics as we know them. For now, its precise identity remains hidden, a tantalizing whisper among the cosmic cacophony. In our quest to understand the composition of the universe, dark energy serves as a reminder of how much there is yet to learn about the cosmos. The pursuit is not just about solving an astrophysical riddle, but also about unraveling the story of existence, the narrative that includes us, our planet, our solar system, and extends to the furthest reaches of the universe. As research unfolds, each new piece of information brings us closer to understanding not just what dark energy is, but what it means for the fate of the universe. Will the universe continue its accelerated expansion indefinitely, eventually dissolving everything into an incredibly vast cold void? Or will some unknown property of dark energy eventually reverse itself, possibly leading to a big crunch? These are not just academic questions, they touch on the very essence of time, space, and reality itself. And so, as we gaze up at the night sky, we are reminded not just of the beauty of the stars, but of the profound mysteries that lie beyond, driven by a force that weaves through the cosmos, a force known as dark energy. Electromagnetism. Electromagnetism represents one of the four fundamental interactions in nature, sitting alongside gravity, the weak nuclear force, and the strong nuclear force. At its core, electromagnetism is the study of the relationship between electricity and magnetism, phenomena that at first glance appear distinct, yet are deeply interwoven. Let us start with the basics. Electricity. It pertains to the presence and flow of electric charge. We see electricity in various forms: static electricity, generated when rubbing a balloon on your hair, or the continuous flow of charges through a wire, powering everything from light bulbs to computers. Magnetism, on the other hand, is the force exerted by magnets when they attract or repel each other. We encounter it when we use a compass, which aligns with the Earth's magnetic field, or when magnets hold notes against our refrigerators. For many years, electricity and magnetism were thought to be separate forces. The unification began in earnest during the early 19th century, when Hans Christian Ørsted made a groundbreaking observation: a compass needle moved when placed near a current-carrying wire, indicating that an electric current generates a magnetic field. Building on this discovery, the British scientist Michael Faraday demonstrated the reverse effect: moving a magnet near a coil of wire induces an electric current in the wire. This principle of electromagnetic induction is the backbone of modern electrical generation, employed in turbines within power stations across the globe. The unification of these forces advanced significantly with James Clerk Maxwell. In the 1860s, Maxwell formulated a set of equations, aptly named Maxwell's equations, describing how electric and magnetic fields interact. He proposed that changes in an electric field would give rise to a magnetic field, and vice versa. These coupled oscillations propagate through space as electromagnetic waves. To express it in a simplified manner, a variation in electric fields generates magnetic fields, and a variation in magnetic fields induces electric fields, perpetuating an endless cycle of wave propagation. One of the most astonishing predictions from Maxwell's equations was the realization that light itself is an electromagnetic wave. His calculations showed that electromagnetic waves travel at speeds matching the measured speed of light, effectively suggesting that visible light is just a small slice of a vast electromagnetic spectrum. This spectrum extends from radio waves with their long wavelengths to gamma rays, which are infinitely more compact. Maxwell's elegant theory not only unified electricity and magnetism, but also laid the groundwork for technological advancements such as radio communications, X-ray imaging, and even the device you are likely using to listen to this video. There's an interesting analogy to consider. Imagine a vast, invisible field, much like a still pond. Introducing an electric or magnetic force is akin to throwing a stone into this pond. Ripples move outward, representing electromagnetic waves. Similarly, these ripples influence everything they encounter, much like how light waves allow us to perceive the world in brilliant color. The unification of electricity and magnetism has permeated every aspect of our daily lives. Wireless communication, MRI machines in healthcare, and the development of alternating current electrical systems all trace back to the fundamental principles of electromagnetism. Moreover, this unified force is central to the exploration of the cosmos. Astrophysicists rely on electromagnetic observations to unlock mysteries of distant galaxies, investigate black holes, and witness the birth of stars. In summary, electromagnetism, the unification of electricity and magnetism, is not merely an intellectual idea, but a profound force shaping the universe and human civilization. Through the elegant interplay of these forces, we've transcended the boundaries of our primitive understanding of the world, leading to innovations that once only existed in the realm of imagination. From the simple compass guiding explorers to the complex technologies that shape our modern world, electromagnetism is a testament to the power of scientific discovery and the enduring quest to understand the fundamental laws governing our universe. Maxwell's equations. Maxwell's equations lay the foundation for our understanding of electromagnetism, a cornerstone of classical physics that ultimately describes how light behaves. Named after the Scottish physicist James Clerk Maxwell, These equations elegantly unify electricity, magnetism, and optics, showing that they are all different manifestations of the same fundamental phenomenon. Let's explore the four equations, one at a time. We begin with Gauss's law. This equation describes the relationship between electric charges and electric fields. It tells us that the electric flux through a closed surface is proportional to the charge enclosed within that surface. Mathematically, the equation is expressed as the integral of the electric field over a closed surface equals the total charge inside divided by the permittivity of free space. Essentially, it conveys that electric charges produce electric fields, acting somewhat like a fountain of electric energy emanating from charges. Next is Gauss's law for magnetism, which is remarkably similar to the first equation, yet it tells a different story. In this case, the equation stipulates that the magnetic flux through a closed surface is zero. Simply put, there are no magnetic monopoles in nature, meaning that every magnetic field line is continuous and never starts or stops in free space. You can think of magnetic field lines like loops of thread. They always form closed loops and do not begin or end on any charge. The third equation is Faraday's law of induction. This principle explains how a changing magnetic field can induce an electric current or voltage. Imagine moving a magnet through a coil of wire. This motion generates an electric current in the wire, a phenomenon harnessed by generators to produce electricity. The law is mathematically described by the integral of the electric field around a closed loop being equal to the negative of the rate of change of the magnetic flux through that loop. Faraday's law gives us insight into the dynamic interplay between electricity and magnetism and is crucial to understanding how transformers and electric motors work. Maxwell added a key component to the final equation, Ampere's law, which deals with magnetism produced by electric currents. In its enhanced form, often called Ampere-Maxwell law, it states that the magnetic field circulating around a closed loop is proportional to the sum of the electric current passing through the loop and the rate of change of the electric field through it. This addition of the changing electric field term, called the displacement current, is what makes electromagnetic waves, like light, possible. It suggests that changing electric fields can generate magnetic fields, and vice versa, allowing these fields to propagate through space in synchronized waves. Together, these four equations form the complete picture of classical electromagnetism. They demonstrate the underlying unity between electric and magnetic fields and show that light itself is an electromagnetic wave, a remarkable insight that opened the door to numerous scientific and technological advancements. To visualize how these equations interconnect, consider a simple analogy. Imagine a pair of dancers moving across a stage. Each dancer represents one of the fields, electric or magnetic. As one dancer steps forward, the other responds, creating a harmonious, intertwined performance. This perpetual dance signifies how changing electric fields generate magnetic fields, and how changing magnetic fields, in turn, generate electric fields. It's a constant exchange, illustrating the propagation of light through space. Maxwell's equations also have profound symmetry, hinting at universal principles that reach beyond electromagnetism. Their elegance lay in their ability to encapsulate complex interactions in a compact mathematical framework, providing a model for modern physics' quest for unified theories. With these equations, we can predict the behavior of electromagnetic fields in a wide range of situations, from the simple act of using a flashlight to the intricate processes occurring in a radio transmitter. This mathematical framework is central to the design of everything from cell phones to medical imaging devices, shaping both the theoretical and practical landscape of modern physics. In summary, Maxwell's equations offer an eloquent description of how electric and magnetic fields interact, revealing the true nature of light. By understanding these principles, we not only unlock the secrets of the electromagnetic spectrum, but also deepen our appreciation for the intrinsic beauty of the physical universe. The Higgs field. In the vast world of particle physics, understanding why particles have mass has puzzled scientists for decades. Enter the Higgs field, a critical concept that helps us unravel this mystery. To grasp the idea, picture a grand ballroom filled with people. Imagine the people as particles moving through the space. In this scenario, the Higgs field is like a dense crowd within the ballroom. Some individuals glide through the crowd effortlessly, while others struggle to pass through, negotiating each step. This friction, the resistance they experience, is akin to what gives particles their mass. The Higgs field itself is an invisible energy field that spans the entire universe. It's not visible to the naked eye, yet it's omnipresent, affecting every particle that interacts with it. Most of us are familiar with fields, such as magnetic or electric fields, whose effects are evident in everyday phenomena. The Higgs field is similar, but its function is more subtle and profound. Particles that interact strongly with the Higgs field exhibit greater mass, while those that interact weakly or not at all remain nearly massless, like photons, which are the particles that make up light. A crucial element of this theory is the Higgs boson, a particle that was predicted by physicists Peter Higgs and his colleagues, and later confirmed by experiments at the Large Hadron Collider. The Higgs boson can be likened to a ripple in the Higgs field. Just as a fish might notice a ripple when a stone is thrown into the water, scientists observed the Higgs boson as a ripple, indicating the existence of the Higgs field. Detecting this ripple was a monumental task. It required the combined efforts of thousands of scientists and sophisticated machinery, capable of slamming particles together at nearly the speed of light. When particles move through the Higgs field, it's akin to a boat sailing across a lake. As the boat moves, it experiences drag due to the water, slowing it down. The mass of a particle is much like this resistance. The more interaction a particle has with the Higgs field, the heavier is the drag, and consequently, the greater the particle's mass. The Higgs field, therefore, bestows mass upon fundamental particles like electrons and quarks, allowing the universe to have the complexity we observe today. Without the Higgs field, particles would zip through the universe at the speed of light, unable to clump together to form the atoms, matter, and ultimately, the diverse structures we see around us. Imagine a universe where the Higgs field didn't exist. It would consist only of light and radiation, without stars, planets, or life as we know it. This theory isn't just preeminently about giving particles mass. It's a pivotal piece in the puzzle of the Standard Model of particle physics. The Standard Model is a comprehensive framework that describes the electromagnetic, weak, and strong nuclear interactions, among others. The inclusion of the Higgs field resolved significant inconsistencies within this model, allowing for a more coherent understanding of how fundamental forces operate. Yet, mysteries remain. We know the Higgs boson exists because it has been observed, but many questions persist. Why does the Higgs field have the particular strength that it does? Why do some particles gain more mass than others? These are profound questions that continue to drive research in particle physics forward. To discover the Higgs boson, an intricate history of scientific endeavor culminated at CERN, where the Large Hadron Collider provided the necessary conditions to observe these fundamental processes. It's an ongoing quest, expanding into realms like dark matter and beyond the Standard Model physics, where the Higgs field's role might yield new revelations. The Higgs field and its interaction with particles are prime examples of how subtle yet foundational mechanisms can lead to the rich complexity of the universe. Without it, the tapestry of existence we experience would be unimaginably different, providing a humbling perspective on the interconnectedness of fundamental physics. As our understanding deepens, so too does our appreciation for the elegant structure that underlies all that we perceive. The Higgs boson. The Higgs boson is often called the God particle, but that nickname is misleading. It's not divine, and it's certainly not magical. What makes the Higgs boson important is that it confirms the existence of something even more fundamental, the Higgs field, an invisible field that fills the universe and gives mass to certain elementary particles. To understand what that means, Let's start with the question, why do particles have mass at all? In the standard model of particle physics, particles like electrons, quarks, and W and Z bosons are initially massless in the theory's equations. But in the real world, we know they do have mass. The Higgs field solves this puzzle. Imagine the Higgs field as a kind of energy sea spread throughout the entire universe. It's everywhere, always present, and it interacts with some particles more strongly than others. As particles move through this field, they experience resistance, not in the sense of friction, but as a kind of drag on their motion. This interaction is what gives them mass. Think of it like walking through a crowd. If you're someone unknown, you can pass through quickly. But if you're famous, people gather around you, slowing you down. In this analogy, the crowd is the Higgs field, and the slowing down is the mass. Some particles interact heavily with the field, like the W and Z bosons, and gain a lot of mass. Others, like photons, pass through unaffected and remain massless. The Higgs boson is the ripple or quantum excitation of the Higgs field. Just like a photon is a particle of light, a Higgs boson is a particle of the Higgs field. Detecting this boson means confirming that the field really exists. For decades, the Higgs boson was a missing piece of the standard model. The theory predicted it, but it had never been observed. That changed in 2012, when scientists at CERN, using the Large Hadron Collider, announced the discovery of a new particle consistent with the Higgs boson. They smashed protons together at extremely high energies, creating the conditions needed for the Higgs to briefly appear. It decayed almost immediately, but its presence was revealed through its decay products and statistical analysis. Finding the Higgs boson was a major breakthrough, but it was also just the beginning. Now that we've confirmed it exists, scientists are trying to study its properties in detail. How strongly does it interact with different particles? Does it behave exactly as predicted, or could it reveal clues about physics beyond the standard model? The Higgs boson is unusual in another way. It's a scalar particle, meaning it has no spin. Most elementary particles have some form of intrinsic angular momentum, or spin. The Higgs does not. It's the only known fundamental scalar particle in nature, and its behavior is unique because of that. It also plays a critical role in the early universe. Shortly after the Big Bang, the Higgs field likely underwent a phase transition. As the universe cooled, the field settled into a lower energy state, and particles suddenly gained mass. Without this process, the universe as we know it would be unrecognizable. Atoms could not form. Stars and galaxies would not exist. Despite its success, the Higgs boson also raises new questions. Why does the Higgs field have the strength it does? Why is the Higgs boson's mass what it is, instead of something much larger or smaller? These are open questions, and they hint at deeper layers of physics we don't yet understand. The discovery of the Higgs boson, it showed that the vacuum of space is not empty. It's filled with a field that shapes the behavior of matter itself. And with that confirmation, we took one more step toward answering one of the oldest questions in science. Why does anything have substance at all? Weak nuclear force. The weak nuclear force, one of the four fundamental forces of nature, plays a crucial, yet often understated role in the universe. Unlike gravity or electromagnetism, which we experience in our daily lives, the weak nuclear force operates inside the heart of atoms, deeply influencing processes that occur at an invisible scale. This force is primarily responsible for governing certain types of particle interactions and is integral to processes like radioactive decay and nuclear fusion. To understand the weak nuclear force, let's first consider its scale and impact. It operates at extremely short ranges, typically less than a fraction of the diameter of a nucleus. Despite its range, it is vital for processes like beta decay, a type of radioactive decay, where a neutron in an unstable atomic nucleus transforms into a proton, emitting an electron and an antineutrino in the process. This transformation showcases the force's ability to change one type of subatomic particle into another, highlighting its unique versatility. Interestingly, the weak force is crucial for the sun's energy production. Deep within the sun's core, nuclear fusion takes place, converting hydrogen into helium and releasing the energy that powers sunlight. A key step in this fusion process involves the weak force. When two protons collide in the sun, they must overcome the repulsive electromagnetic force due to their positive charges. Once close enough, the strong nuclear force encourages them to stay together. However, to initiate fusion, one proton must transform into a neutron. This is where the weak nuclear force comes into play, enabling the proton to neutron transformation and allowing them to bind together, forming deuterium and releasing energy. This transformation leads to the eventual production of helium from hydrogen, with an immense release of energy in the form of radiation, which fights against gravitational collapse and supports the star. Without the weak nuclear force, the sun and all stars could not shine. They wouldn't have the necessary mechanism to convert hydrogen into helium efficiently. Furthermore, it's essential to recognize that the weak nuclear force is mediated by particles known as W and Z bosons. These bosons are massive compared to other particles that mediate forces, like the photon for electromagnetic forces. The mass of the W and Z bosons is vital to the short range and overall weakness of the force. Their large mass means they can only exist for a very short time and travel only a short distance, which is why the weak force is limited in range. In the broader context of the universe's formation, the weak force also contributed significantly during the early moments following the Big Bang. During this time, the universe was hot and dense, allowing the weak force to play a substantial role in particle interactions, leading to the formation of the first atomic nuclei. Understanding these processes provides insight into the conditions of the early universe and the forces that shaped its evolution. The weak nuclear force is often seen as the lesser-known sibling among the fundamental forces, but its impact is profound. It is a force of change, allowing for the transmutation of particles and making stellar energy generation possible. Our understanding of it is crucial for fields such as particle physics and cosmology, helping scientists explain the behavior of matter under extreme conditions. The weak force is a testament to the intricate mechanisms that operate at the heart of matter, subtly guiding the symphony of atomic transformations that create and power the universe we observe today. Strong nuclear force. The strong nuclear force, often referred to as the strong force, is one of the fundamental forces of nature and the one that operates at the smallest scales. It acts like the glue that holds the nucleus of an atom together, overcoming the electromagnetic repulsion between the positively charged protons within the tightly confined space of an atomic nucleus. To understand its role, let's dive into the world of subatomic particles, where this force exhibits its dominance. At the heart of every atom is the nucleus, composed of protons and neutrons, collectively known as nucleons. Protons are positively charged, and neutrons carry no charge. Under normal conditions, like charges repel each other. Considering this, you might wonder why protons don't simply fly apart due to their mutual repulsion. The answer lies in the strong nuclear force, which is a powerful force, but with very short range. Unlike gravity or electromagnetism, which have infinite ranges, the strong force operates effectively only over distances on the order of 1 femtometer, which is 1 million-billionth of a meter. This force is carried by particles known as gluons, which facilitate the interaction between quarks, the smaller constituents of protons and neutrons. In essence, gluons are the exchange particles that carry the force between quarks, keeping them tightly bound within the nucleons, and in turn, holding the nucleons together within the nucleus. If quarks are like the bricks that make up protons and neutrons, then gluons are the mortar that holds the bricks together. An often used analogy is that of a rubber band. Imagine trying to pull apart a tightly stretched rubber band. The more you pull, the greater the force it exerts to snap back together. The strong nuclear force operates similarly. It becomes stronger as quarks move further apart, preventing them from being isolated. This characteristic is known as confinement, and it explains why quarks are never found alone in nature. They are always confined within larger particles like protons and neutrons. The strength of this force can be illustrated by comparing it to other fundamental forces. It is about 100 times stronger than electromagnetism, which is responsible for holding atoms and molecules together by the attraction between opposite charges. It is also much stronger than the weak nuclear force, which governs processes like radioactive decay, and countless times stronger than gravity, which is the force of attraction between masses. Despite its strength, the strong nuclear force has a crucial limitation: its extremely short range. Once beyond the nuclear scale, the force effectively becomes invisible and plays no significant role in our everyday macroscopic world. This shortfall in range is also why atoms can exist with such a variety of elements with stable nuclei, even those as large as uranium. Quantum chromodynamics, or QCD, is the theory that describes how the strong nuclear force works. In this framework, quarks carry a type of charge called color charge, analogous to electric charge in electromagnetism, but with three types referred to as red, green, and blue, and their corresponding anticolors. Gluons themselves carry color charge and constantly exchange between quarks, maintaining the attractive interaction that keeps them bound together. These interactions are incredibly complex, and simulating them requires the use of powerful supercomputers. The strong nuclear force is vital to the fabric of the universe, as we know it. Without it, atomic nuclei would not exist, and neither would the subsequent atoms and molecules that form stars, planets, and life. Nuclear fusion, the process that powers the sun and stars, relies on this force to overcome the repulsion between hydrogen nuclei until they fuse into helium, releasing vast amounts of energy. Thus, while often unseen and unappreciated in the everyday macroscopic world, the strong nuclear force plays a critical role behind the scenes. It not only ensures the stability of matter at the atomic level, but also drives cosmological processes that have shaped the universe over billions of years. Our understanding of this force continues to evolve, offering insights into both the very small, like the workings of particles, and the very large, like the formation of the elements in stars. Fundamental interactions. Our universe is governed by forces that dictate how particles interact with one another, weaving the fabric of everything we observe in nature. These are known as the four fundamental interactions or forces. They are the gravitational force, electromagnetic force, strong nuclear force. Each of these forces plays a unique and critical role in shaping the universe, from the way stars shine to the structure of atoms. Let's begin with the gravitational force. This force is probably the most familiar, as it's the one we experience in our everyday lives. Gravity is the attraction between two masses. Imagine the Earth and the Moon. Their masses pull on one another, which keeps the Moon in orbit around the Earth. This was eloquently described by Isaac Newton, who stated that this force is proportional to the product of the two masses and inversely proportional to the square of the distance between their centers. In simple terms, if you double the mass of one of the objects, the gravitational pull doubles. If you double the distance between them, the force becomes 1/4 as strong. Gravity also played a crucial role in forming galaxies, stars, and planets by enabling the clumping together of matter in the early universe under its uniform pull. Next, we have the electromagnetic force. This force acts between charged particles. It's responsible for almost everything we observe at the molecular and atomic level, including light. While the gravitational force acts on mass, electromagnetic force acts on anything with charge. We live in a world where opposites attract, so positive and negative charges pull together, while like charges repel each other. A simple demonstration of this can be seen when rubbing a balloon on your hair. The balloon becomes charged and then can stick to a wall, a dance of attraction and repulsion governed by electromagnetism. Unlike gravity, which only attracts, Electromagnetic force can both attract and repel, giving it a broader range of influence on the structure of atoms and molecules. The strong nuclear force, as the name suggests, is incredibly strong, but it acts over a very short range. It operates at the heart of the atom, binding protons and neutrons together in the nucleus. Without it, the positively charged protons would repel each other due to electromagnetic force, and the nucleus would fly apart. The intense strength of the strong nuclear force explains why the energy released in nuclear reactions, such as those in the sun or nuclear power plants, is so immense. This force is what ultimately powers the stars, including our sun, through nuclear fusion, providing the energy essential for life on Earth. Finally, the weak nuclear force might sound less impressive compared to the others, but it plays a key role in processes such as nuclear decay and is crucial to the sun's production of energy through fusion. The weak force is responsible for the process known as beta decay, a type of radioactivity where a neutron in an unstable nucleus is transformed into a proton, emitting an electron, and an antineutrino in the process. Without the weak nuclear force, stars wouldn't be able to produce heavier elements, as it allows protons and neutrons to transform into one another in the fusion process, keeping the balance needed for the stars to shine brightly. These interactions create a balance that crafts the universe we know, from the formation of galaxies to the chemistry of life. They hold the cosmos together. Despite their ubiquity, these forces operate out of plain sight, revealing themselves through effects and phenomena that we can observe. Scientists are continually probing deeper to unify these interactions into a single coherent theory, a pursuit that holds the promise of understanding the intricacies of the universe at its most fundamental level. As we look around us, in every sunrise, every leaf, and every star lies a dance, choreographed by these incredible forces, shaping everything from the colossal structures of the cosmos to the microscopic world within each atom. Superconductivity. Superconductivity is a remarkable phenomenon where certain materials, when cooled to very low temperatures, conduct electricity with zero resistance. Not just low resistance, zero. That means once an electrical current starts flowing in a superconductor, it can keep going indefinitely without losing any energy as heat. In everyday materials, like copper or aluminum, resistance is always present. As electrons move through the metal, they scatter off atoms and imperfections in the material. This scattering turns some of the electrical energy into heat. That's why wires get warm, and power is lost during transmission. But in a superconductor, that scattering disappears. The electrons flow as a perfectly coordinated stream. The discovery of superconductivity happened in 1911, when a Dutch physicist named Heike Kamerlingh was studying the electrical properties of mercury at low temperatures. As he cooled the mercury close to absolute zero, he noticed something extraordinary. Its resistance suddenly dropped to zero. This wasn't a gradual reduction. It was a sharp, complete transition. Mercury had become a superconductor. Since then, scientists have discovered many other materials that exhibit superconductivity, including certain ceramics and alloys. The temperatures needed to achieve superconductivity vary, depending on the material, but in all known cases, they're extremely cold, usually just a few degrees above absolute zero. So how does it work? The key lies in the behavior of electrons inside the material. In a normal conductor, electrons behave like individuals. They collide with atoms and other electrons, which causes resistance. But in a superconductor, something strange happens. The electrons begin to form pairs. These are called Cooper pairs, named after physicist Leon Cooper. You might expect electrons, which carry the same negative charge, to repel each other, and they do. But in certain conditions, the vibrations of the atomic lattice can actually create an attractive force between them. This allows the electrons to pair up. Once paired, they move through the material in a coordinated way, without scattering. It's a quantum effect, and it allows the entire system to behave like a single coherent wave. Superconductivity also leads to another fascinating effect. the expulsion of magnetic fields. When a material becomes superconducting, it actively pushes magnetic fields out of its interior. This is known as the Meissner effect. It's the reason a magnet can levitate above a superconducting surface. The magnetic field lines are repelled, and the magnet floats on an invisible cushion. Superconductors have many practical applications. They're used in magnetic resonance imaging, or MRI machines, which require strong and stable magnetic fields. They're also used in particle accelerators, where powerful magnets are needed to steer high-energy particles. And they have the potential to revolutionize energy transmission, allowing electricity to flow over long distances without any loss. But there's a major challenge. Most superconductors require cooling with liquid helium or liquid nitrogen, an expensive and complex process. Scientists have been searching for materials that become superconducting at higher temperatures. These are called high-temperature superconductors, and some have been found that work at around -135 degrees Celsius. That's still cold, but much more practical than the temperatures near absolute zero. The ultimate goal is to find a room temperature superconductor. If that could be achieved, it would change everything. Power grids with no energy loss, maglev trains that float frictionlessly, ultra-efficient electronic circuits, and perhaps entirely new forms of quantum devices. Superconductivity is one of the clearest examples of how quantum mechanics can show up in large, visible systems. It's not just an effect happening at the level of atoms or molecules. It's something you can measure, see, and use. It reminds us that nature, under the right conditions, can behave in ways that defy our everyday expectations. And in those rare and quiet corners of the coldest laboratories, electrons reveal a hidden order where energy flows forever without resistance. Superfluidity. Superfluidity is a quantum phenomenon where a liquid flows without any resistance. Not low resistance, none at all. In a superfluid, there's no friction, no viscosity, and no energy loss. Once the fluid starts moving, it keeps moving without slowing down indefinitely. It's one of the most striking demonstrations of quantum mechanics at a macroscopic scale. The most well-known example of a superfluid is liquid helium. When helium-4 is cooled below a certain critical temperature, about 2.17 Kelvin, it undergoes a dramatic transformation. It stops behaving like an ordinary liquid and becomes a superfluid. This state is sometimes called helium-2. You can see the effects of this transformation with your own eyes. In a famous demonstration, liquid helium in an open container will begin to creep up the walls and spill over the sides. It forms a thin film and flows continuously, even against gravity. Place it in a closed loop and set it moving, and it will circulate forever. No pumps, no losses, just perfect, frictionless flow. This behavior doesn't make sense in classical physics. Ordinary fluids always experience some drag, but superfluidity arises from the same principles behind Bose-Einstein condensation. In fact, helium-4 atoms are bosons, and at ultra-low temperatures, they begin to occupy the same quantum ground state. They behave not as individual particles, but as a single coherent wave. In a superfluid, the atoms move in perfect coordination. There's no scattering, no turbulence, and no internal friction. The fluid becomes, in a sense, more like a quantum object than a collection of atoms. One of the most interesting consequences of superfluidity is the formation of quantized vortices. In a normal fluid, you can create a swirling vortex of any size or strength, but in a superfluid, rotation is constrained. The fluid can only rotate in fixed, discrete units, like steps on a ladder. These are called quantized vortices, and they form neat, well-defined patterns. Unlike the messy swirls of classical turbulence, superfluidity isn't limited to helium-4. Helium-3, which is a fermion rather than a boson, can also become superfluid at even lower temperatures. But in that case, the mechanism is more complex. Helium-3 atoms first pair up to form composite bosons, Similar to how electrons form Cooper pairs in superconductors, these pairs can then condense into a superfluid state. Studying helium-3 superfluidity has helped scientists explore connections between quantum fluids, superconductivity, and even models of the early universe. Superfluidity also shows up in other extreme environments, like the cores of neutron stars. These stars are incredibly dense, with matter compressed to unimaginable levels. Under those conditions, it's believed that neutrons form a superfluid, and protons form a type of superconductor. These exotic quantum states affect the way neutron stars cool, spin, and emit radiation. In the lab, superfluid systems allow scientists to simulate aspects of quantum mechanics in ways that are otherwise difficult to observe. They offer a playground for studying collective quantum behavior, coherence, and topological effects. Even though superfluids exist at ultra-cold temperatures, their behavior is surprisingly robust. Once formed, they resist being disturbed. In fact, you can spin a superfluid and create persistent currents that last for hours, days, or longer, without any input of energy. Superfluidity is not just about strange liquid behavior. It's about what happens when quantum rules take over the macroscopic world. When the chaotic motion of particles disappears and a new kind of order emerges. It reminds us that even in the quietest, coldest corners of the universe, nature can surprise us. And in that surprise, we catch a glimpse of the underlying unity between matter, motion, and the mysterious laws of quantum physics. Bose-Einstein Condensate. The Bose-Einstein Condensate is one of the most fascinating and counterintuitive states of matter ever discovered. It's what happens when certain particles are cooled to temperatures just a tiny fraction above absolute zero. Under these extreme conditions, matter begins to behave not like a collection of individual atoms, but like a single, unified quantum entity. To understand what makes a Bose-Einstein condensate so special, we need to talk about the particles involved, bosons. In quantum physics, all particles are classified as either fermions or bosons. Fermions, like electrons and protons, obey the Pauli exclusion principle, which means they can't occupy the same quantum state. But bosons follow very different rules. Multiple bosons can occupy the same state without restriction. In fact, they prefer it. This tendency to crowd into the same state is the basis for the Bose-Einstein condensate, first predicted in the 1920s by Satyendra Nath Bose and Albert Einstein. They theorized that if you take a gas of bosonic atoms and cool it down far enough, the atoms will begin to collapse into the same lowest energy state. Instead of acting like separate particles, they all begin to behave as one. It took over 70 years before this theory was confirmed in the lab. In 1995, researchers in Colorado created the first Bose-Einstein condensate using rubidium atoms. They used lasers and magnetic traps to cool the atoms to less than a billionth of a degree above absolute zero. At that point, the atoms lost their individual identities and merged into a single quantum wave. What makes a Bose-Einstein condensate so remarkable is that it behaves more like a wave than a gas. All the atoms are described by the same wave function. This means they move in sync, with zero relative motion between them. In a sense, the entire collection of atoms acts like one giant superatom. One way to visualize this is to imagine a room full of dancers. At high temperatures, each dancer moves independently, spinning and turning in their own way. But as the temperature drops, they begin to synchronize. Eventually, all of them move in perfect unison, as if guided by a single choreographer. That's similar to what happens in a Bose-Einstein condensate. The random, chaotic motion of particles disappears, and a new kind of order emerges. This state of matter is incredibly delicate. Even the slightest disturbance, such as a rise in temperature or interaction with the environment, can cause the condensate to break apart. But while it lasts, it offers a unique glimpse into the quantum world at a macroscopic scale. Bose-Einstein condensates are more than just scientific curiosities. They're being used to study superfluidity, where a fluid flows with zero viscosity. They also help us understand coherence, interference, and other quantum behaviors that are usually hidden at higher temperatures. Because the condensate behaves as a single quantum object, it becomes a perfect system for testing the limits of quantum mechanics. Some researchers have even used Bose-Einstein Condensates to simulate conditions in the early universe, black hole analogues, and exotic materials. And although they are challenging to produce, they've opened an entirely new branch of physics, ultra-cold atomic physics, where the line between matter and wave begins to blur. At its core, the Bose-Einstein Condensate challenges our classical intuition. It shows that when particles lose their individuality and enter a shared quantum state, a new kind of matter can emerge, one that behaves according to the strange, beautiful rules of quantum physics. It reminds us that even something as familiar as a gas can become something entirely different under the right conditions. And it proves that in the quiet cold of the quantum world, nature has more surprises in store than we ever imagined. Fermionic condensates. Fermionic condensates are a special state of matter formed by particles called fermions, cooled to temperatures extremely close to absolute zero. They are one of the most unusual phases of matter ever created in a laboratory, and they offer a window into the quantum world, where the normal rules of physics no longer apply. To understand what makes fermionic condensates so special, we first need to understand what a fermion is. In particle physics, all matter particles fall into two broad categories: fermions and bosons. Fermions include electrons, protons, and neutrons, the building blocks of atoms. One of the key features of fermions is that they obey what's called the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state at the same time. This rule explains why electrons in atoms fill up distinct energy levels and don't all collapse into the lowest energy state. It also explains why matter has structure and stability. Without this principle, atoms couldn't exist in their familiar form, because fermions resist crowding into the same state. It's very difficult to make them act collectively, unlike bosons, which can all pile into the same state and form a Bose-Einstein condensate. Fermions naturally avoid each other, but under the right conditions, we can coax them into behaving in pairs. And when they form these pairs, they start acting more like bosons. That's the key to creating a fermionic condensate. This idea isn't just theoretical, it's the same principle that underlies superconductivity, the phenomenon where certain materials conduct electricity with zero resistance. In a superconductor, electrons pair up into what are called Cooper pairs. These pairs are not subject to the Pauli exclusion principle in the same way individual electrons are. As a result, they can move through a material without scattering, allowing for perfect electrical flow. Fermionic condensates take this idea further. In an ultra-cold gas of fermionic atoms, cooled to just a few billionths of a degree above absolute zero, the atoms can also form pairs. These pairs then condense into a collective quantum state, where they begin to act as a single coherent entity. The system behaves like a quantum fluid, with properties that are completely different from those of the individual particles that make it up. The first fermionic condensates were created in the early 2000s, using isotopes of potassium and lithium. Physicists used lasers and magnetic traps to cool the atoms and manipulate their interactions. What they observed was a smooth transition from a gas of individual fermions into a paired superfluid state, a fermionic condensate. One of the fascinating things about these systems is that they can be tuned by adjusting external fields. Scientists can control how strongly the fermions interact. This makes fermionic condensates a powerful laboratory for studying quantum many-body physics, with applications that go beyond atomic gases. For example, studying fermionic condensates can help us understand neutron stars, dense remnants of supernova explosions that are packed with fermions under extreme conditions. It also helps shed light on high-temperature superconductors, which remain one of the biggest puzzles in condensed matter physics. Fermionic condensates are not materials you can touch or hold. They exist in controlled environments at unimaginably low temperatures, but they represent a profound achievement, taking individual quantum particles that naturally resist cooperation and guiding them into a state of perfect collective order. They show us that even the most fundamental building blocks of matter can exhibit new and surprising behavior when pushed to their limits. And they remind us that the quantum world still holds many secrets, some of them waiting quietly at the coldest edges of the universe. String theory. String theory is one of the most ambitious and far-reaching ideas in modern theoretical physics. It proposes that the fundamental building blocks of nature are not particles, but tiny, vibrating strings, so small that they are far beyond the reach of any current experiment. These strings are not made of anything smaller. They are considered fundamental, and the way they vibrate determines what kind of particle they appear to be. In ordinary physics, particles like electrons, photons, and quarks are treated as point-like objects with no size, just positions and properties. But in string theory, each of those particles is actually a loop or segment of string. The difference between an electron and a photon isn't what the string is made of, but how it vibrates. One mode of vibration might correspond to a photon. Another mode might represent a quark. The energy and pattern of the vibration determine the mass and charge of the resulting particle. One of the most exciting aspects of string theory is that it naturally includes gravity. In fact, the graviton, the hypothetical particle that carries the force of gravity, emerges directly from certain vibrational modes of the string. This is important because gravity has been the most difficult force to reconcile with quantum mechanics. String theory offers a framework that might finally unite gravity with the other forces: electromagnetism, the strong nuclear force, and the weak nuclear force. But there's a catch. For string theory to work mathematically, it requires more dimensions than we can see. In our everyday experience, we observe 3 dimensions of space and 1 of time, but string theory requires 10 spatial dimensions, plus time, 11 in total if you include the version known as M-theory. The extra dimensions are thought to be compactified, meaning they are curled up so tightly that they are invisible to us, like threads wrapped around a surface too small to detect. These hidden dimensions are not just mathematical tricks. Their shape and structure determine the physical properties of our universe. The way they are curled can affect the kinds of particles that exist, their interactions, and even the values of physical constants. This leads to an enormous number of possible configurations, sometimes estimated as 10 to the 500. Each one describes a different possible universe, with its own rules. This landscape of possibilities has led some scientists to consider whether our universe might be just one among many. String theory also introduces objects beyond strings, such as branes, short for membranes. These are higher dimensional analogues of strings, and our entire universe could be a 3-dimensional brane floating in a higher dimensional space. In this view, gravity can leak into the extra dimensions, while the other forces are confined to our brane. This might explain why gravity is so much weaker than the other fundamental forces. Despite its elegance, string theory remains a theory without experimental confirmation. It makes very few testable predictions that we can currently verify. The strings are thought to be on the order of the Planck length, which is about 1.6 times 10 to the minus 35 meters. That's far smaller than anything we can probe with existing technology. Still, the mathematical structure of string theory has led to remarkable insights in other areas of physics. It has helped physicists understand black hole, entropy, quantum field theory, and even connections between gravity and quantum information. Some of its tools have crossed into other disciplines, offering new ways to solve old problems. String theory is not just a proposal about tiny vibrating loops. It's an attempt to unify all of physics in a single consistent framework, a theory of everything. It may or may not be the final answer, but it has already transformed how we think about space, time, matter, and the deepest structure of reality. Whether it turns out to describe our universe or not, string theory reminds us that the foundations of nature may be far stranger and far more beautiful than anything we've yet imagined. M theory. M theory is one of the most ambitious ideas in theoretical physics. It aims to unify all the fundamental forces and particles in the universe into a single framework, a theory of everything. It builds on string theory, but goes a step further, proposing that our universe may have more dimensions than we can see, and that the fundamental building blocks of reality are not particles or even strings, but extended objects that exist in higher dimensions. To understand where M theory comes from, we need to look at string theory first. String theory proposes that the smallest constituents of nature are not point-like particles, but tiny vibrating strings. Each mode of vibration corresponds to a different particle. One vibration gives rise to an electron. Another gives rise to a quark. Yet another might represent a graviton, the hypothetical quantum of gravity. In this way, string theory naturally includes gravity, something that most other quantum theories struggle to do. But string theory isn't just one theory. In fact, during the late 20th century, physicists discovered several different versions of string theory. Each seemed mathematically consistent, but they appeared to describe different universes with different rules. For a while, it seemed that instead of one elegant theory, there were 5 competing models. Then, in the mid-1990s, something unexpected happened. Physicists began to discover connections between these different versions. What looked like separate theories were actually related, linked by mathematical transformations that allowed one to be transformed into another. These connections suggested that all 5 string theories were actually different perspectives on a deeper, more fundamental theory. Something more comprehensive, that deeper framework, was given the name M theory. What the MA stands for is deliberately ambiguous. Some say it means membrane, because M theory includes not just one-dimensional strings, but also higher-dimensional objects called branes. Others say it stands for mother, mystery, or even magic, reflecting the theory's far-reaching and still uncertain nature. In M theory, the universe is not limited to the familiar 3 dimensions of space and 1 of time. Instead, there are 11 dimensions in total. 7 of these extra dimensions are thought to be compact and curled up so tightly that they are undetectable at human scales. But their shapes determine the properties of particles and forces, and changing those shapes can lead to entirely different physical laws. The inclusion of membranes, or branes, is one of M theory's most distinctive features. A brane can have any number of dimensions. Our entire universe could be a 3-dimensional brane floating in a higher dimensional space, sometimes called the bulk. In this view, particles are the endpoints of strings stuck to our brane, while gravity, which is tied to closed strings, can leak into the extra dimensions. This could explain why gravity is so much weaker than the other fundamental forces. M theory is still a work in progress. It is not yet fully formulated, and many of its predictions remain beyond the reach of current experiments. But it offers a powerful mathematical structure that unifies different string theories and brings together quantum mechanics and gravity in a way that no other theory has done successfully. One area where M theory has had influence is in the study of black holes. Using tools from M theory, physicists have been able to count the microscopic configurations that make up certain kinds of black holes and recover their entropy, the measure of disorder, exactly as predicted by general relativity. This is one of the rare places where a quantum theory of gravity has matched classical predictions perfectly. M theory also appears in speculative models of cosmology. Some scenarios suggest that our universe began when 2 branes collided, releasing energy that triggered a Big Bang. In others, The extra dimensions evolve over time, influencing the behavior of particles and fields in ways we are only beginning to understand. Despite its complexity, the goal of M-theory is simple: to find a single coherent framework that describes all of nature's forces and particles in a unified way. Whether it ultimately succeeds or not, it has already transformed our understanding of space, time, and the possible structure of reality. M-theory may still be a mystery, but it's one of the most promising attempts to glimpse the full architecture of the universe. Brane Cosmology. Brane Cosmology is a fascinating branch of theoretical physics that seeks to explain the universe using concepts beyond our standard three-dimensional understanding. The term brane comes from membrane, and in this context, it refers to multidimensional sheets that exist in higher dimensional space. To imagine this, picture our universe laid out on a two-dimensional sheet, similar to a vast, thin piece of paper. However, unlike paper, these branes are not flat or static. They can be curved, dynamic, and exist in spaces with more than 3 dimensions. In string theory, one of the leading proponents of brane cosmology, our known universe sits on a 3-dimensional brane in a higher dimensional space, often referred to as the bulk. This bulk can have additional dimensions, sometimes many more than we can perceive. For instance, superstring theory, which is one approach within string theory, proposes a total of 10 dimensions, while M-theory suggests 11. Our universe encompasses 4 of those dimensions, 3 spatial and 1 temporal, but the others are compactified, meaning they are curled up so small that they are imperceptible to us. Now let's consider what this means for cosmology, the study of the universe's origin, structure, evolution, and eventual fate. According to brane cosmology, other branes might exist parallel to ours within this higher dimensional bulk. These could harbor their own universes, potentially with their own unique laws of physics. Just as there are sheets in a ream of paper, countless universes could exist, separated by a fraction of a dimension, but entirely apart from what we know. An analogy that might clarify this involves considering an ant walking on the surface of a garden hose. To the ant, the hose appears two-dimensional, forward and backward, left and right. But we, as three-dimensional beings, understand that the hose extends into a third dimension, allowing movement around its circumference. The hose is akin to a compactified extra dimension. If more dimensions exist, and if they affect the fundamental forces, it might, hypothetically, be possible for effects or objects to leak between branes. One of the intriguing ideas in brane cosmology is the interaction between branes, where universes can influence one another. Some theories propose that colossal cosmic events, such as the Big Bang that started our universe, could result from branes colliding or coming close enough to transfer energy. This brane collision idea offers an alternative to singularity-based models of the universe's creation, addressing some of the limitations and paradoxes associated with the traditional Big Bang theory. Moreover, brane cosmology might provide insights into the long-standing hierarchy problem in physics, which puzzles over why gravity is so much weaker than the other fundamental forces we observe. The weakness of gravity in our universe could be due to its interaction with other dimensions, dissipating across the bulk rather than being confined to our universe alone. Imagine sound emanating from a speaker in an open space. The sound dissipates and weakens as it travels further. Similarly, gravity might spread out across these additional unseen dimensions. While compelling, brane cosmology remains largely theoretical. The scientific community continues to grapple with ways to empirically test or observe aspects of these higher dimensions and branes. The differences between theoretical frameworks that include branes and those that don't are subtle, especially at energies and scales we can currently measure. Efforts such as those at the Large Hadron Collider, aiming to detect signs of extra dimensions through high-energy particle collisions, could yield important insights. The mathematical elegance of brane cosmology makes it an appealing area of study, potentially unifying differing physical theories under a broader, more complete framework. But much remains to be done to determine how well it fits our observations of the universe. For now, Brane Cosmology represents a powerful idea that extends our imagination beyond the familiar confines of space-time, challenging us to think of reality as a vast tapestry woven with more threads and patterns than the mind can ordinarily conceive. Quantum gravity. Quantum gravity represents one of the most intriguing and challenging areas of modern theoretical physics. At the heart of this field is a quest to understand how the universe operates on both large and small scales, because the current theories of quantum mechanics and general relativity are famous for their mutual incompatibility. Quantum mechanics brilliantly describes the universe's smallest particles and forces, while general relativity offers profound insight into its vast cosmos. Yet, unifying these two pillars in a cohesive framework remains elusive. Imagine trying to fit a puzzle piece from two separate puzzles into a single picture. In one corner, there's general relativity, a theory developed by Albert Einstein in the early 20th century. It describes gravity not as a traditional force, but as a curvature of space-time surrounding massive objects. Consider how a trampoline stretches and dips when you stand in the middle. This is akin to how the mass of a planet like Earth warps the fabric of space around it, guiding smaller celestial bodies to orbit it. In the realm of the extremely small, quantum mechanics reigns supreme. This domain governs the particles making up atoms and the fundamental forces acting upon them. Here, uncertainty plays a key role. Particles can exist in a superposition or multiple states simultaneously. On this tiny scale, probabilities replace certainties, and events are described not by determined paths, but by a range of potential outcomes. Just like rolling a pair of dice, where different results emerge every time, quantum mechanics demands statistical descriptions of physical states. However, these two theories create tension when placed side by side. Quantum field theory, a framework for interaction at the quantum level, struggles to incorporate the gravitational force described by general relativity. The problem arises because gravity also asserts itself at very small scales, influencing particles' behavior in ways not fully understood within quantum frameworks. Delving deeper, consider the center of a black hole where all the known laws of physics break down. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. Within their cores, known as singularities, densities reach infinity, creating a standout example of quantum mechanics and general relativity's divide. Efforts to reconcile these differences have birthed fascinating theories. String theory is one such attempt. It imagines that every fundamental particle is not a point, but a tiny vibrating string. These strings' vibrations determine the particle's properties, much like different tension or length changes a guitar string's note. In this theory, gravity arises naturally, integrated within the framework, as one of the possible vibrational tones. However, string theory requires more dimensions than we perceive, suggesting a universe with up to 11 dimensions squeezed into our perceived reality. Another intriguing approach is loop quantum gravity. Rather than treating gravity as continuous, like a smooth basketball surface, it considers space-time to consist of tiny, indivisible loops. These loops weave the fabric of space in eternally interlocking, discrete networks formed by quantum bits, known as qubits. Picture a mosaic made out of tiles, where each tile represents a segment of space-time. Even the passage of time emerges from the interactions of these fundamental quantum tiles. Despite theoretical strides, experimental validation remains one of quantum gravity's foremost challenges. Experiments conducted in laboratory settings currently lack the energy levels to directly probe these quantum gravitational effects. Instead, physicists rely on astronomical phenomena, such as black holes or gravitational waves, to indirectly explore quantum gravity. The detection of gravitational waves, ripples in space-time caused by cataclysmic cosmic events, has provided critical insights into gravitational interactions, albeit mostly within classical frameworks. Future technologies may yet develop the precision necessary to observe quantum-scale gravitational phenomena, marking a crucial step in our search for understanding the universe's fundamental framework. Quantum gravity thus embarks on a profound journey, striving to interlace the tapestries of general relativity and quantum mechanics into a unified picture of nature. Like a grand unifying melody, this quest seeks to harmonize the cacophony of physical laws governing large galaxies and tiny particles into a single cohesive symphony. Although this endeavor stands at the frontier of scientific exploration, it offers the tantalizing prospect of comprehending the universe's deepest secrets. Loop quantum gravity. Loop quantum gravity is a theory that attempts to answer one of the deepest questions in physics: how can we describe gravity using the rules of quantum mechanics? General relativity explains gravity as the curvature of space-time, and quantum mechanics explains the behavior of particles and forces at the smallest scales. But putting the two together has proven to be one of the greatest challenges in modern science. Loop quantum gravity, often shortened to LQG, is one of the main approaches to solving this problem. Unlike string theory, which introduces extra dimensions and new types of particles, loop quantum gravity sticks more closely to the familiar structure of space and time. Its central idea is that space itself is not continuous. Instead, it is made up of tiny discrete chunks, like the pixels on a screen, but even smaller and more fundamental. According to this theory, space is composed of loops. These loops are not material objects. They are mathematical structures that describe how space is woven together at the quantum level. The loops are connected in networks, called spin networks, which define the structure of space at a given instant. As time progresses, these networks evolve, forming what are known as spin foams. Together, they describe how space-time emerges from quantum geometry. The loops themselves are incredibly small, on the order of the Planck length, which is about 1.6 times 10 to the minus 35 meters. At this scale, the smooth fabric of space-time, described by general relativity, breaks down. Instead, what we get is a granular structure where space is made of finite units, and geometry becomes quantized. One of the key achievements of loop quantum gravity is that it provides a way to describe gravity without requiring a background space. In most physical theories, space is assumed to already exist, and fields or particles live within it. But in loop quantum gravity, space is built from the theory itself. This background independence is a central feature of general relativity, and loop quantum gravity preserves it in a quantum framework. The equations of loop quantum gravity suggest that areas and volumes are not continuous, but take on discrete values. That means there's a smallest possible unit of area and a smallest possible volume. You cannot divide space endlessly. Below a certain scale, the idea of distance no longer makes sense in the usual way. This leads to some profound consequences. For example, loop quantum gravity offers a new way to think about black holes. In classical general relativity, black holes have singularities, points where the curvature of space-time becomes infinite. But in loop quantum gravity, the granular nature of space prevents this infinite collapse. Instead of a singularity, the core of a black hole might be a region of extremely curved, but finite, space, perhaps even connecting to another region of the universe. The theory also makes predictions about the early universe. In loop quantum cosmology, the Big Bang is replaced by what's called a big bounce. Rather than emerging from a singularity, the universe may have gone through a prior phase of contraction, followed by a rebound into expansion. This idea is still being studied, but it offers a possible way to avoid the infinities that plague classical cosmology. Loop quantum gravity is not yet a complete or unified theory. It does not currently explain all the particles and forces seen in nature, and it has not yet made specific predictions that can be tested experimentally. But it provides a mathematically consistent and conceptually elegant framework for thinking about quantum space-time. What makes loop quantum gravity compelling is its simplicity. It does not rely on extra dimensions or unobservable entities. It starts with the basic idea that space and time are made of something, that the smooth fabric of the universe is, at its core, woven from loops. Whether or not this theory turns out to be the final answer, it pushes us toward a deeper understanding of reality. It reminds us that space may not be empty, and time may not be smooth. They could be built from quantum ingredients, stitched together into the universe we live in. Theory of everything. The quest for a theory of everything is one of the most ambitious endeavors in the realm of physics. This theory seeks to encapsulate the fundamental laws governing the universe into a single, all-encompassing framework. It's often referred to as the Holy Grail of physics because it aims to unify two major pillars of science, general relativity and quantum mechanics. General relativity, developed by Albert Einstein, describes the gravitational force as a curvature of space and time caused by mass. Imagine a trampoline with a heavy ball placed in the center, creating a dip. Smaller balls placed on the fabric will naturally roll towards the depression, illustrating how gravity affects objects within its field. This theory successfully explains the motion of planets, the bending of light around stars, and even the expansion of the universe at cosmic scales. On the other hand, quantum mechanics delves into the subatomic world, describing the behavior of particles at incredibly small scales, where the rules of classical physics break down. In this quantum realm, particles like electrons and photons exhibit both wave-like and particle-like properties. They exist in states of probability, where their properties are not defined until measured. The famous double-slit experiment underscores this duality, where particles create an interference pattern, akin to waves, when not observed, but behave like distinct particles when measured. Despite their profound success in their respective domains, general relativity and quantum mechanics appear to be fundamentally incompatible. General relativity is deterministic, meaning it predicts the future perfectly if the present conditions are known. Quantum mechanics, conversely, is probabilistic, dealing in likelihoods rather than certainties. This discord presents a challenge when trying to merge these theories into a cohesive framework. For instance, when attempting to describe the interior of black holes or the conditions of the universe at the moment of the Big Bang, both theories converge to regimes where they fail to provide logical answers. The ambition to resolve these inconsistencies has guided physicists towards developing a unified framework. One promising candidate is string theory. Unlike traditional particle physics, which views particles as point-like entities, string theory proposes that fundamental particles are actually one-dimensional strings. These strings can vibrate at different frequencies, with each mode of vibration corresponding to a different particle. Picture the strings of a violin. Each string can produce a distinct note, and correspondingly, in string theory, the specific vibrations of strings determine the properties of the particles they represent. String theory introduces extra dimensions beyond the familiar 3 dimensions of space and 1 of time. It suggests there could be up to 11 dimensions, most of which are compactified or hidden from our direct perception. These extra dimensions could hold the key to reconciling the equations of general relativity with those of quantum mechanics, offering a unified description of all forces and particles in the universe. Apart from string theory, another approach is the concept of loop quantum gravity. This theory attempts to merge quantum mechanics with general relativity by suggesting that space-time itself has a discrete structure, much like a fine mesh or grid, composed of tiny loops interconnected to form a fabric. Unlike string theory, loop quantum gravity does not assume any additional dimensions, focusing instead on quantizing space-time itself. However, both string theory and loop quantum gravity, among other candidate theories, remain mathematical and conceptual frameworks at this stage. Experimental evidence is needed to validate any proposed theory of everything, but testing these theories poses significant challenges due to the energy scales and conditions required, which are far beyond our current technological capabilities. The pursuit of a theory of everything is not just about unifying equations. It forms a deeper philosophical quest to understand the universe's nature and our place within it. The process pushes the boundaries of human knowledge, offering glimpses into the elegant simplicity and profound complexity underlying all existence. While the journey toward this ultimate theory is fraught with theoretical challenges and unknowns, it continues to inspire generations of physicists to explore the very fabric of reality. Symmetry breaking. And symmetry breaking is a concept that plays a central role in modern physics. It helps explain how a universe that once appeared perfectly balanced could give rise to the complexity and structure we see today. At its core, symmetry breaking describes a process where something that starts out in a highly symmetrical state ends up in a state that is less symmetrical, but more interesting. In physics, symmetry means that the laws of nature stay the same under certain transformations. For example, if you rotate a perfect circle, it still looks the same. That's rotational symmetry. If the physical laws remain unchanged whether you look left or right, or whether a particle moves forward or backward in time, those are symmetries too. But our universe, as we observe it, is not perfectly symmetrical. Particles have different masses. Forces behave differently, galaxies form structures, and not everything is evenly distributed. So, what happened? The answer lies in the idea of spontaneous symmetry breaking. To understand this, imagine a pencil perfectly balanced on its tip. In theory, it's symmetrical in every direction, but the moment it falls, it chooses a direction, any direction, at random. The laws that govern the pencil don't change, but the outcome is no longer symmetrical. That's spontaneous symmetry breaking. The system starts in a balanced state, but ends up in an unbalanced one, even though the underlying rules remain the same. A more visual example is a round table with a ball placed exactly in the center. The system is perfectly symmetric, but if the ball rolls toward one edge, that symmetry is broken. The ball's movement selects a direction, even though the table itself didn't favor one. In particle physics, symmetry breaking explains many of the differences we see among fundamental particles. For instance, in the early universe, just after the Big Bang, it's believed that all fundamental forces were unified, part of a single symmetrical force. But as the universe cooled and expanded, this symmetry broke. Forces that were once the same split into distinct forces: gravity, electromagnetism, the strong force, and the weak force. One of the most important examples of symmetry breaking in physics involves the Higgs field. Before symmetry breaking, particles had no mass. They all behaved as if massless. But as the universe cooled, the Higgs field settled into a lower energy state, and particles began to interact with it. This interaction gave them mass. The symmetry of the high energy state was broken, and in its place, we got the diverse set of particles we observe today. This is called electroweak symmetry breaking, and it's a cornerstone of the Standard Model. Symmetry breaking also shows up in condensed matter physics. In materials like magnets, the atoms start in a disordered, symmetric arrangement at high temperatures. As the material cools, the atoms align in a particular direction, breaking that symmetry and creating a magnetic field. The concept even applies beyond physics. In biology, for example, many organisms start life with a symmetrical structure, but over time break that symmetry to develop a head and tail, or left and right sides. In nature, symmetry is often associated with potential. Breaking that symmetry is what gives rise to structure, function, and identity. What makes symmetry breaking so profound is that it explains how complexity can emerge from simplicity. The rules stay the same, but the outcomes become rich and varied. It's the reason particles have mass. It's why forces behave differently. It's how a universe that began in perfect balance gave rise to stars, planets, and life. In physics, symmetry is beautiful, but it's the breaking of symmetry that creates reality as we know it. It turns smooth into structured, uniform into unique, and in doing so, it unlocks the diversity of the universe. The Anthropic Principle. Imagine you are floating in a universe, vast, infinite, and filled with wonders. Among the myriad of possibilities in which you could find yourself, there's one profound question: why does our universe, with its precise conditions, permit life? Enter the Anthropic Principle, a philosophical consideration that attempts to address this intriguing mystery. The Anthropic Principle suggests that the universe's fundamental properties are as they are because they allow for the existence of observers like us. It's a framework for understanding that the universe is not random, but instead has conditions that align with the existence of life. The principle comes in several forms: weak, strong, and everything in between. But all versions share the common idea that our presence influences how we perceive the universe's properties. The weak version of the Anthropic Principle states that the universe's observed values of the physical constants are restricted by the requirement to allow for life as we know it. It simply indicates that certain conditions must hold for us to observe the universe, and those conditions happen to align with life-permitting values. For instance, consider the fine-tuned nature of the gravitational constant. If it was slightly stronger, stars would burn out too quickly to allow life to develop. If it were a bit weaker, stars wouldn't form the necessary complex elements in their cores. Another striking example is the electromagnetic force. It's crucial for holding atoms and molecules together. Adjust its strength slightly, and atoms wouldn't survive, or life-sustaining chemistry would be impossible. The universe is a delicate balance of forces and constants, orchestrated in such a way that life can exist in its intricate forms. The strong version takes this a step further, suggesting that the universe must have properties that eventually lead to the emergence of conscious life. This intriguing claim raises questions about the nature of reality and our place within it. Is the universe a purposeful construct with the goal of creating life? Or is our existence a mere statistical happenstance in a multiverse teeming with varied cosmic laws? The Anthropic Principle goes beyond mere speculation. It pushes us to consider why these constants have such finely tuned values. Some propose that there are many universes, each with different values of constants. In most, life cannot emerge, while in a select few, the conditions are just right. This multiverse view implies that our universe is simply one in a vast array where the peculiar recipe of physical laws permits the emergence of observers. Alternatively, consider the analogy of a selection process. Think of an archer shooting arrows at a distant target, a vast wall of possible universes. Each arrow represents a unique set of physical laws. Imagine you find yourself standing in front of a bullseye where there are numerous arrows clustered closely. You would likely conclude that either many arrows were shot or the archer was incredibly skilled. Similarly, in the cosmic shooting range, either there are countless attempts in the form of multiple universes, or there's an inherent design aiming specifically for a life-permitting universe. Critics of the Anthropic Principle argue it doesn't provide a falsifiable scientific hypothesis. By its nature, it's retrospective, explaining why we observe what we do, but offering little predictive power. It's a philosophical layer applied atop the universe's scientific understanding, similar to how a building's architecture provides context to the layout underneath. Yet, this principle serves an essential purpose. It opens a dialogue about the nature of reality and invites scientists and philosophers to probe deeper into the cosmic order. As we contemplate the universe's architecture, we realize the Anthropic Principle is not about reducing our sense of wonder, but about framing it in the context of existential inquiry. This principle bridges the gap between the observed universe and the reason we exist to observe it. It encapsulates the curious situation of our existence and underscores why we ponder these lofty questions. As we gaze at the stars, we must consider not just the how, but the why. It's this profound pursuit of understanding that defines our journey through the cosmos. CPT Symmetry. CPT symmetry is a fundamental principle in physics that says the laws of nature remain unchanged if we reverse three things at the same time: charge, parity, and time. That's what the letters stand for. C is for charge, which means switching particles with their oppositely charged counterparts. P is for parity, which means flipping the spatial coordinates, like turning a system into its mirror image. And T is for time, which means running a process backward, as if you were rewinding the universe like a film. Individually, these operations can sometimes break the rules. That is, there are known physical processes where the symmetry fails if you only apply one or two of these transformations. But when you apply all three together, charge, parity, and time, the theory says that the combined system should behave exactly the same. This principle is not just a guess. It's built into the mathematics of quantum field theory, the same framework that underpins the Standard Model. Let's break it down a little further. Charge conjugation means replacing a particle with its antiparticle. If you take an electron and swap it for a positron, which is identical in every way, except that it has a positive charge, you're performing charge conjugation. Some physical laws look the same under this transformation, but not all. For example, weak nuclear interactions do not obey charge symmetry on their own. Parity transformation means flipping the spatial axes, turning left into right, and vice versa. Imagine watching a physical process in a mirror. For a long time, physicists thought all processes would look the same in a mirror. But in the 1950s, experiments showed that certain subatomic decays look different when viewed in a mirror. So parity symmetry, on its own, is also broken by the weak interaction. Time reversal means playing a process backward. If you filmed a bouncing ball and reversed the footage, it would still make sense physically. But for certain quantum processes, especially those involving particle decays, running the sequence in reverse doesn't follow the same rules. That means time symmetry can also be broken. But here's the remarkable part. Even though charge symmetry, parity symmetry, and time symmetry can each be broken individually and even in pairs, when you combine all three, C, P, and T, the universe seems to restore balance. The full set of laws remains invariant under this combined transformation. This is CPT symmetry. CPT symmetry is not just a curiosity, it's a deep requirement of any relativistic quantum field theory that obeys certain basic conditions like locality and energy conservation. If a theory violates CPT symmetry, it usually means something is seriously wrong with its underlying structure. The most practical implication of CPT symmetry is that particles and antiparticles must have the same mass and the same lifetime. If an electron and a positron didn't behave this way, it would indicate a breakdown of CPT symmetry, and that would signal a need for entirely new physics. So far, every experiment we've done supports the principle. No violations of CPT symmetry have ever been observed. This doesn't mean the concept is simple. The fact that charge, mirror symmetry, and time flow can be individually violated while still preserving the overall symmetry is deeply non-intuitive. It hints at how tightly woven the laws of nature really are, and how certain balances are preserved, even when others are broken. CPT symmetry also plays a role in some of the biggest questions in cosmology. For example, why does the universe contain more matter than antimatter? Since CPT symmetry insists that matter and antimatter should behave symmetrically under combined transformations, the observed imbalance is still a mystery. Physicists are exploring whether tiny violations of related symmetries could explain what happened in the early universe. In short, CPT symmetry is a kind of anchor in the quantum world. It tells us that even in a universe full of strange asymmetries, some things remain perfectly balanced, no matter which direction you look, which particles you use, or even which way time is flowing. The multiverse. The multiverse is the idea that our universe might not be the only one. Instead, it could be just one region, one bubble, within a much larger reality that contains many other universes, each with its own laws of physics, constants, and possibilities. It's a concept that stretches the imagination, but it also arises naturally from several well-established areas of theoretical physics. One place where the idea of a multiverse shows up is in cosmology. specifically in the theory of cosmic inflation. This theory proposes that in the very early moments after the Big Bang, the universe expanded incredibly rapidly, far faster than the speed of light. This expansion smoothed out space and set the stage for everything we observe today. But in some versions of inflation theory, that rapid expansion never completely ends. Instead, it continues in different regions, creating what's called eternal inflation. In this model, our universe is just one bubble, where inflation stopped, while countless other bubbles continue forming elsewhere, each becoming its own universe. Another version of the multiverse comes from string theory, a candidate for a theory of everything. String theory requires extra dimensions of space, dimensions we don't see in daily life, because they're thought to be compact and curled up at very small scales. But there are many ways these extra dimensions could be shaped, and each shape leads to a different set of physical laws. The result is a vast landscape of possible universes, potentially as many as 10 to the 500. In that scenario, our universe is just one version where the conditions happened to support stars, chemistry, and life. Then there's the quantum mechanical perspective. In one interpretation of quantum theory, called the many worlds interpretation, every quantum event causes the universe to split into multiple branches. If a particle can go left or right, it does both, but in separate universes. According to this view, every possible outcome of every event actually happens, but in a different branch of the multiverse. The world you experience is just one thread in this vast quantum tapestry. These different multiverse models vary in detail, but they all share a central idea that what we see as the universe may not be all there is. There could be other universes, unreachable from our own, each with its own story, its own physics, and possibly even its own version of you. Of course, the multiverse is controversial. One reason is that, by definition, other universes are not observable, at least not directly. We can't travel to them or send signals. That makes the idea difficult to test, and some scientists argue that it falls outside the boundaries of science. Others believe that, if a well-tested theory, like inflation or quantum mechanics, naturally leads to a multiverse, then we should take that prediction seriously, even if it challenges our ability to measure it. The multiverse also raises deep philosophical questions. If there are countless universes, each with different physical laws, what makes ours special? Why do we live in a universe where the constants of nature happen to allow for stars, planets, and conscious observers? Some scientists invoke the Anthropic Principle, which says that we can only observe a universe compatible with life, because if it weren't, we wouldn't be here to ask the question. Whether or not the multiverse is real, thinking about it helps us understand just how limited our perspective might be. For centuries, humans believed Earth was the center of everything. Then we discovered it was just one planet orbiting a star, which was just one star in a galaxy, among billions of galaxies. The multiverse idea takes that one step further. It suggests that even our entire universe may be just one region in a much larger and richer cosmic structure. We may never know for certain if other universes exist, but the fact that serious scientific theories predict them tells us something important, that the universe we see may be only a small part of reality, and that reality, as strange as it may sound, could be far bigger and more diverse than we ever imagined. Open questions in physics. Despite all the breakthroughs in modern science, physics is still full of mysteries. Our current theories, like the Standard Model of particle physics and general relativity, have been remarkably successful, but they're not complete. There are questions we still can't answer, and problems we don't yet know how to solve. These open questions represent the frontiers of our understanding. They are the puzzles that continue to push science forward. One of the biggest mysteries is dark matter. Observations of galaxies show that stars move as if there's far more mass present than we can see. That extra mass is called dark matter. It doesn't emit light, it doesn't reflect it, and it doesn't interact with ordinary matter in any direct way, except through gravity. We know it must be there, but we don't know what it is made of. It could be a new kind of particle. It might be something even stranger. Despite decades of searching, dark matter remains invisible. Another major puzzle is dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is speeding up. That was unexpected. The force causing this acceleration is called dark energy. It seems to make up more than 2/3 of the total energy in the universe, but we know almost nothing about it. Is it a property of space itself? Is it something that changes over time? Or is it a sign that our understanding of gravity is incomplete? Then there's the challenge of unifying quantum mechanics and general relativity. Quantum mechanics governs the smallest scales, like atoms and subatomic particles. General relativity describes the largest scales, planets, stars, and galaxies. Both theories work incredibly well on their own, but they don't fit together. When we try to apply both theories at once, such as near a black hole or at the beginning of the universe, the math breaks down. A complete theory of quantum gravity is one of the holy grails of physics. The origin of the universe is also an open question. We have a solid understanding of what happened shortly after the Big Bang, but we don't know what triggered the event or what existed, if anything, before it. Some models suggest a previous universe or a cosmic bounce. Others suggest time itself began at the Big Bang, but none of these ideas are confirmed. We also don't know why the constants of nature have the values they do. The mass of the electron, the strength of gravity, the speed of light, these values appear to be finely tuned. Slight changes would make the universe hostile to atoms, stars, or life. Is this a coincidence? Is there a deeper reason for these values? Or are they set randomly in a multiverse, with our universe being one of many? The nature of time is another deep mystery. Why does time seem to flow in one direction? The laws of physics work equally well forward and backward in time, but our experience tells us time moves only forward. This arrow of time is tied to entropy and the spread of disorder, but the full explanation remains elusive. And what about consciousness? While this question overlaps with neuroscience and philosophy, it also touches on physics. Is consciousness an emergent property of matter, or does it reveal something more fundamental about the universe? Some physicists have wondered whether new physics might be needed to fully explain awareness and experience. Finally, there's the possibility that our current theories are just approximations. Just as Newtonian physics gave way to relativity and quantum mechanics, our current models might be part of a deeper, more unified picture. We don't yet know what that deeper picture looks like. Open questions in physics are not signs of failure, they are signs of progress. They show us where the edges of our knowledge lie, and each unanswered question is an invitation to explore, to experiment, and to rethink what we thought we knew. In science, the unknown is not a wall, it's a doorway. And in physics, that doorway still leads to vast and unexplored territory.